On. Okay. Molly, I don't think the mic is on yet, so she was just chatting. Should we good? Okay. Good morning, everyone. We're going to get going in just 2 minutes or so. Just some quick housekeeping announcements. Just a reminder, the official parking is in P22, which is sort of just to the west of here. I can't guarantee if you didn't park in P22 that you might not get ticketed. So if you didn't, maybe make your way back at some point this morning and move your vehicle. If you have questions about where that is, just let me know. In terms of restrooms, if you go out here in the main atrium and then just go down the atrium about 100 feet to the left, the restrooms are there. And I think that's the main things you need to know. So otherwise, we'll get started. So I'm happy to introduce Frank Moses from Skaneateles Lake Association.
Great, thanks, Steve. We have quite a few folks online as well. So just a couple extra housekeeping for folks joining online. There is a Q&A button that if you have any questions during today, please go ahead and ask. We do have very limited time. We're going through a lot of short round robins. So we may not get to everybody's questions. So for folks online, if you want to indicate who your question is specifically for, that'll help us do some follow-up and make sure we help get that answer for you, hopefully in a few days or less than a week we'll shoot for. But wanted to say good morning and Happy New Year to everyone. Welcome to the Skaneateles Lake Research and Data Summit. This is our second one of doing these. We did one just shy of the pandemic back in January 2020. I see some familiar faces. So it's great that we get to start this up again. It's wonderful to see so many folks that are online today. I think we had about about 70 plus registrants and ticking as of last night. And it's truly heartwarming to see this room filled with people who care deeply about one of the most extraordinary lakes in the world that is quintessential to our local livelihood. Whether you're a researcher, a partner organization, a policymaker, a volunteer, or a neighbor who simply loves this lake, your presence here speaks volume about the kind of community we are and our collective dedication towards safeguarding future generations. Skaneateles Lake, like many others, are facing three major threats, as I like to put things in buckets. First, we're facing the growing pressure of excessive nutrient loading. Even small increases in nutrients can tip a lake like ours towards harmful algal blooms, degraded water quality, and cascading ecological impacts. Nutrient loading is sometimes subtle, cumulative, and often invisible, and sometimes not. Like these gully gushers of chocolate milk, and then we see the blooms that can follow. Here's a couple aerial shots and some flooding damage that maybe looks very familiar to other folks visiting from other lakes. I did want to note we have, I think, representation online and in this room from each of our Finger Lakes and the New York State Federation of Lake Associations. So these are the threats that we all share. Secondly, we confront the accelerating impact of invasive species. These organisms disrupt the ecological balance that has defined Skaneateles Lake for generations. They alter food webs, stress native species, and change the very character of the lake's nearshore and deep water environments. And third, we must contend with persistent contaminants, including forever chemicals that do not break down, do not disappear, and do not have easy remedies. These contaminants challenge our assumptions about safety, treatment, and long-term stewardship. These three threats, nutrients, invasives, and contaminants, are not abstract. They are real, measurable, and already shaping the lake's trajectory, but they are not insurmountable, and we are seeing at least 2 out of the 3 are linked to the threat of harmful algal blooms that are exacerbated by climate change and development pressures. The Skaneateles Lake Association is responding with determination and a deep commitment to partnership. We are working directly and indirectly through partners with residents, farmers, boaters, businesses, municipalities, and regional leaders to reduce nutrient inputs. A lot of them here today, thank you. They prevent the spread of invasives and better understand the sources and pathways of emerging contaminants. We are strengthening prevention, expanding monitoring, and building a culture of shared responsibility across the entire watershed. But to be clear, we cannot do this alone. And more importantly, we cannot do this without science. Science is our compass. It helps us understand the nature of the threats, the tools available to counter them, and the strategies most likely to succeed. Science gives us the metrics to measure progress, to know when we are on the right path, and to celebrate the milestones that reinforce our momentum. It keeps us honest, focused, and grounded in reality rather than assumption. That's why today matters. This summit is not just a gathering, it's a commitment to learning, to collaboration, and to the belief of informed action can protect what we love. We are ever thankful for those who support SLA, the academics, and other efforts for the lake, especially individuals like Sam and Carol Nappy and many others behind academia and SLA's Legacy Fund, which is helping support today. Wanted to thank very much Charlie Driscoll with SU, everyone that's been part of this, Steve Shaw, for bringing this together. Want to express my deep gratitude for all these experts, you today who've joined us, researchers, practitioners, and innovators who dedicate your talents to understanding and protecting freshwater systems. Your work is essential, and your willingness to share it with us strengthens our entire region. I want to thank all of you for being here today. And now it's my honor to reintroduce Steve Shaw, who's embodied this very spirit of scientific partnership we rely on. Dr. Stephen Shaw is the co-director of the Healthy Water Solutions Center of Excellence here at ESF and at Clarkson. With his partners, Dr. Shaw is not only a respected scientist, he is a dedicated ally to Skaneateles Lake, helping us better understand its dynamics, its vulnerabilities, and its remarkable resilience. Please join me in welcoming Steve, our moderator for today's summit and a true champion for healthy waters. Thanks, Steve. I appreciate you and everything you've done.
Thanks for the kind words, Frank. That's a nice way to start the morning. I don't usually get that. So I think we'll get right into our program. We kind of have a nice mix of different talks. Just a little bit organizationally, the first few are a little more focused on sort of the physical features of the lake, and then the later ones are more about sort of nutrient loading in multiple different ways. But otherwise, it's really a nice kind of mix of different things, of a lot of really cool research that's been done really just in the last few years. In terms of the talks, the speakers will basically have between 15 and 20 minutes in most cases, and then we'll leave a few minutes at the end for questions. It is a little tight, we'll kind of keep it moving, but really for people here in person, the afternoon and lunch is really our time for discussion, and we'll have plenty of that in the afternoon. I will mention then for the speakers, just, we're academics, so we like to explain what we're doing, but there will be a 2-minute warning and a 30-second warning. So we ask when you see those to start wrapping things up. Okay, so we'll just get going. So first speaker we have is Dr. Christopher Schultz from Syracuse University, who'll be talking about bathymetric mapping of the lake. Okay, it looks like we're in business.
Thanks, Steve.
Yeah.
Thanks, Steve. Thanks, Frank and Charlie, for organizing this really nice event today. It's a pleasure to present to you today some of the work that we've been carrying out since last spring, investigating the lake bed of Skaneateles Lake. Just a quick shout out to the science team that's really been doing the heavy lifting here. Doug Woods, our lead analyst, who's been directing the field program and leading the data processing, as well as Nick Brennan, who's also here, a doctoral student who's going to be doing the lion's share of the analytical work moving forward. Right, so why bother studying the lake bed, right? It's, we don't see it very easily from the shoreline. We see a little bit, but we've got all this information about the watershed itself. We've got all these fantastic GIS layers where we've characterized aspects of the catchment, but we don't know that very much about what's going on underneath that water column. But it is the sink or the sump for all the discharge coming off the land surface, right? So that's where all of our pollutants are ending up. So we need to have some sense of what's going on down there. And knowing the first order, knowing the shape of the lake bed is really important. It can provide information for man-made infrastructure. It's important for characterizing the water budget and undertaking hydrodynamic analyses of the system. It can help calibrate some of our drone and satellite imagery. We get information on shipwrecks. It can improve navigation. As a geologist, it's important to study the lake bed because we can get a sense of the bottom type, the different sediment grain textures, the type of vegetation that extends across the bottom gives us information about bottom habitat for both native or introduced species. Our particular project is keen to understand the extent of nutrient-rich sediment reservoirs. We know that from previous work, and Charlie and Mike Kelly are going to talk about this work shortly, we know that phosphorus abundance in the sediment increases dramatically as you get into slightly deeper water. As you get into water depths of 15, 20, 25 meters, there's a fourfold increase in the abundance of phosphorus in the sediment. So if there are mechanisms, like Mike will describe shortly, for bringing those nutrient-rich sediments into the upper waters, we have a forcing mechanism for potentially producing very significant harmful algal blooms. Right, so the key questions for our study, our science study, are where are these high nutrient bottom sediments exactly? And to determine that, we need to know the shape of the lake bed, and we need to know the extent of the so-called wash zone or erosion zone that is present in the northern end of Skaneateles Lake. It's actually present at the northern ends of almost all of the Finger Lakes, in our opinion. And this erosion is not a consequence of normal wave action, but it's a consequence of breaking internal waves that we'll hear about further. But there's other things we can learn from mapping the bathymetry of the lake bed, where we pose the question, are there deep water pockmark areas in Skaneateles Lake similar to what have been described and observed in Seneca Lake? Is there any evidence for underwater landslides in the system? I mean, this is actually a non-trivial risk of near-field tsunamis in enclosed lake basins. These kinds of events have been described in many lakes around the world. And for geologists, we're interested to learn if there are features from the glacial era or perhaps the earliest phases of Skaneateles Lake. So just a quick reminder here, we've got Skaneateles Valley was 20,000 years ago, 18,000 years ago, was completely covered by ice. Our whole region, of course, was completely covered by a continental ice sheet. Upwards of 2 miles thick ice covered our area and completely transformed our landscape. Over time, over a period of perhaps 5,000 years or more, that ice front retreated from Long Island and northern New Jersey and moved northward, melted northward into the Finger Lake valleys. And for at least several hundred years, perhaps even a couple of thousand years, there was a massive wall of ice right at the northern end or at the ends of all the Finger Lakes. And we call this the proglacial lake phase of this system. And the landscape was completely altered, of course. There was a tremendous amount of sediment that washed into these valleys during that phase of the lake. And then perhaps beginning around 11,000 years ago, the ice moved out of the catchment completely, and we had this gradual transformation to what we know as modern Skaneateles Lake, this beautiful oligotrophic system. Right, so that's kind of the backstory for a lot of the imaging that we're carrying out here. So in 2025, we carried out this bathymetry and backscatter survey of the lake using a multi-beam echo sounder, and this This technique uses acoustic energy to scan the lake bed in broad swaths. We actually can image the lake bed over a distance, a given swath that's about 3 times the water depth over which the boat is surveying in. And over on the right side of the screen, you can see the survey tracks from our project in July and August. We spent about almost 6 weeks out on the SLA research boat, the Bob, acquiring these data. And you'll notice that the survey tracks are far more concentrated in shallow waters, right? Because it takes much longer to cover that terrain, whereas the deeper waters we can cover relatively quickly. The swaths are that much wider. Right, so we collected 3 main data sets or sample sets over this past field season, and they yielded the lake bed bathymetry, right? We know the shape of the lake bed now. We've also collected this backscatter information or reflectance information, which gives us information on bottom type. And we also collected a series of lake bed samples in slightly deeper water than had been available previously. And Charlie Driscoll is going to speak about some of those analyses in his talk this afternoon. So we've completed the bathymetric data analysis and the sample collection. The backscatter processing is now underway to investigate the type of bottom that we find across the area, and we're also starting off the geochemical analyses on the sediment samples. So I'll mention that very briefly. Right, so there was previous bathymetric information from the lake, but it was relatively crude data. Actually, our team collected this almost 25 years ago, and that data was acquired with an uncalibrated seismic profiler. It was not a hydrographic survey instrument. It was what we refer to as sort of single beam sampling with relatively widely spaced survey lines, required interpolation between those lines, and it didn't include any backscatter information. Whereas our current survey uses this calibrated hydrographic survey instrument. As we're collecting the data, we're also making casts in the water column, measuring sound speed and temperature, so we can make for corrections of sound energy refraction in the water column. And so this multi-beam swath bathymetry tool sends out more than 1,000 beams to the sides of the vessel, and it gives us complete overlapping coverage. And we can produce a digital terrain model of the bottom. And nominally, right now, we have a data set of the entire lake of a 1 meter grid, and in some areas we have even finer than that. And we're in the process, as I mentioned, we're in the process of starting the processing of the backscatter bottom type analysis here. So just a couple examples that I'd like to show you. This is a bathymetric DTM of the area right around the city of Syracuse water intake. And don't worry, Rich, we filtered this out of the main data set. We're not going to share the location of this guy, but you can see quite clearly position of this. And it's quite informative. And the texture that you can see all around the water pipe itself is in fact real lake bed sediment texture or geology through there. So there's a lot of information available. So this map shows the entire data set that we acquired and processed, combined with LIDAR data, that is light imaging radar data from the state of New York. And we observed a maximum water depth of about 87 meters that is observed off of the Fall Brook area in the central southern part of the lake. And it's, you can see quite clearly in here you can see if I can make this guy work. You can see the very steep sides of the southern parts of the basin. Right through there, there's this gradual shoaling margin. I'm not sure this guy is really showing up. You can see that shoaling margin to the north end. That turns out to be very important in terms of nutrient loading. And also we have these shallow shelves at the very northernmost and southernmost parts of the lake. Those shelves weren't there prior to the installation of the dam in the early 1800s, right? Those were swamplands, basically. So that's a very significant change in the character of the lake, and that has implications for water column processes. And perhaps Charlie will touch on some of that later this afternoon. Just another example of some of the data, some of the observations from the bathymetry work. This is, on the left side, you can see a detail of the bathymetry off of Sevi's Marina there, and you can see a number of these significant distributary channels in the system. And if we look at the backscatter of this area, you can see the strong contrast in bottom type from within those channels to the inner channel areas. So the lighter colors are coarser grain sediments being delivered right off of that stream that's coming in right at Sevi's, right through there. So there's a lot of detail in some of these data. If we move up to the north, sort of the central part of the lake off of 5 Mile Point, we notice some very interesting textures in the bottom of the basin. And if we zoom in, we can see a series of these pockmark structures all through this area. If I zoom in a little further, you can see some of the details. These are about 100 meters wide or so. On the right side of the screen, we have a high-resolution seismic reflection profile. It's another acoustic image, not of the lake bed, but of a slice of the sub-bottom. And we can see the deep divot just adjacent to these big pockmarks right through here. These are similar, these features are similar to what are observed and widespread, actually, in the southern part of Seneca Lake. That information is just being published by the group at Middlebury College. We're not entirely sure about the origin of these structures. They're very likely related to processes of ice retreat and glaciation. Perhaps they're ice collapse structures. Has been suggested that they may be associated with groundwater discharge or even gas discharge. Some folks may have heard about the Seneca drums that are legendary in Seneca Lake that are postulated to be a consequence of methane gas eruptions from that system. So this warrants further research, especially if they may be associated with groundwater discharge or perhaps even saline water discharge from salt formations in the subsurface. So we see a number of really interesting features in the northern ends of the lake. We can just in the far north, we've got the drumlin that extends off of 1 Mile Point, off of the country club that's very prominent in the lake bed right through there. The wash zone, the erosion zone, is present all through this northern area. And as I mentioned, we're just starting the processing of the backscatter data, but we also see from our seismic reflection data that some of this lake bed is in fact underlain not by modern lake sediments, but some of those proglacial lake sediments that have been exposed due to these internal breaking waves. A number of other interesting features here. Shotwell Creek Delta is very prominent in this part of the basin. It's built out considerably across the lake bed here. But we also see some interesting features that are related to much earlier phases of sedimentation in the basin going back probably 13,000 years. We can make out very clearly a sinuous ridge, which we interpret to be a glacial esker. These are stream deposits that accumulated underneath the glacial ice sheet, right, when there was thick ice in the system. So we see this high sinuosity ridge extending for, a kilometer and a half or more on the bottom of the lake. It's sticking up above the lake bed. Also a very prominent knob, which we interpret to be a came, another type of glacial till deposit in this particular system. And the sketch on the lower right is a conceptual model of these of the accumulation of these kinds of materials. Right. There's also some examples in different places of significant in-lake landslides. So we can see both off of Jenny Point and Staghorn Point, several of these deposits here. And our hope is to return to this area with our seismic profiler and our sediment cores this coming summer and determine the age of these slides and look at them in a little more detail. As I said, it has been shown in other lake systems that in-lake slides can actually produce non-trivial wash-up as a consequence of nearshore tsunamis in these kinds of environments. So we want to investigate this a little bit more carefully. Another example of a in-lake slide just north of 5 Mile Point in this system. Right. So I mentioned that we also collected some sediment samples during our summer field campaign. The green triangles are data that we acquired several years ago, part of Mackenzie Brannon's doctoral thesis. And I think both Mike and Charlie are going to make mention of the data from those green triangles, and also this pink hexagon down here is the site where we've carried out a historical nutrient study, which is the focus of Charlie's presentation this afternoon. But the white squares are the samples across this erosion zone that we collected this summer. So we are just starting out some geochemical and sedimentological analyses of those samples to determine how enriched they are in phosphorus, how enriched they are in organic constituents. And we'll also characterize the texture of those sediments. So the plan here is to use these sample sets to calibrate our backscatter data to really map out precisely the extent of that nutrient-rich lake bed zone, that wash zone, if you will. Right, so just a summary of the main products from the study. We've completed essentially the main bathymetric mapping and processing work. We're going to be producing an atlas of lake bed bottom type and character, and also carrying out geochemical analyses of these lake bed sediments. And these results will be provided in the form of internal reports to SLA, and we'll continue to work at these outreach events, and we expect a couple of peer-reviewed publications to emerge from this work over the next several years. I did want to mention that we shared the initial data set with a local mapping company east of nowhere, and they are famous for combining geographic information with artwork, and you can purchase a map of Skaneateles on the lake bed from them if you so wish. But we'll release the primary bathymetric data later this year. Initially, a 10-meter grid will be released and put into the state archives. And then as the peer-reviewed publications emerge, we'll release the high-resolution results of that grid. Right, so thank you very much. Stay tuned for further deliverables and outcomes from this work. We're really excited about it. And again, thanks to SLA, to the NAPPIs, and various institutions that have supported the work.
We have about 5 minutes for questions. If you have a question, I'd ask people to step up to the microphone. So online, listeners can also hear that question. The microphone's open. Feel free to hop on.
Thank you so much. Pretty exciting maps of the bottom of the lake. I think I asked this question earlier, but how much is the spatial resolution of the bathymetric map?
Right, so we've processed to 1 meter so far for the entire lake. So we have a 1 meter grid for the entire lake. Selected areas, we've produced some preliminary maps at 0.5 and 0.25 meters.
And one other quick question is, where there are aquatic vegetation, how does this impact your sonar backscatter?
Oh, that's a great question. I mean, we can make some casual observations about where we have vegetation now. It definitely impacts reflectance of the data. We've not yet quantified those observations, so that's kind of work that's forthcoming. For sure, we'll be able to map out areas of significant vegetation in the shallow waters. Yeah.
Good morning, and thank you, Dr. Shaw, for a most interesting presentation. My question, do you think the rapidity of the glacial retreat presents any particular features in Skaneateles Lake and or the Finger Lakes generally? Thank you.
That's an interesting question. we actually don't know how fast the ice moved out of the basin. It's been speculated that it's on the order of as short as just a few hundred years to retreat, across the entire system. It's a question I'd love to dive into a little deeper, but to really refine that is kind of a heavy lift, right? Because we need deep samples to really determine the timing of that full-on retreat. It's not surprising that it was relatively quick, but based upon the fact we're seeing these subglacial features in the basin, suggests that it retreated fast, and there was a proglacial lake there immediately. So we didn't erode those eskers or those cames, those other features in there. So based upon what we've seen in the seismic reflection data from Skaneateles and other lakes, this remotely sensed acoustic sub-bottom profile information, 500 years to maybe 1,500 years might be a reasonable estimate for the time of retreat there, but it's still kind of speculation.
Is there any photographic evidence of the nature of the swamps at the north and south ends of Skaneateles Lake? In other words, the nature of the way the land looked at the north end of Skaneateles Lake before the dam went in?
Right.
And the south end?
Yeah, that's a great question. Well, we have our acoustic imagery, right? But there's no, it's been speculated, or if you go into the historical literature, there's documentation of wetlands all across that area, right? It was swampland before the establishment of those dams in the early and mid 19th century. So it's completely altered, right? There's no more vegetation down there. We have a lot of hard ground, carbonate cemented sediment for the most part. So it'd be worth diving a little deeper, though, into the acoustic information to see if there's any relict information. There's a lot of interesting phenomena down there. I'll just show you one other image. This is backscatter information off of 1 Mile Point, off of the drumlins. We have all these weird donut-shaped features all across this area. And if anybody has any idea what have produced these, they're about 3 meters in diameter, right? And they're very distinctive. It almost looks like it was a mooring field or something at some point in the past. If anybody knows anything about the history of the lake and can share some insights, I'd be really delighted to hear about it. It's an area I'd like to go scuba diving on this coming season to actually see what's down there. So there's a lot of interesting stuff that we just don't know about, and we need to drill a little deeper into the data sets. Thanks very much.
Okay, next up we have Dr. Mike Kelly from RPI.
Thank you very much for being here, everyone, and a tremendous thanks to SLA for hosting this. Frank, thank you. And Dr. Shaw for arranging, Charlie and Chris. What I'd like to talk about today is some data that we collected in 2018 and in a resulting paper that we put out in July of 24. See if I can do this right here. Okay, so this project started, my understanding is that toxic cyanobacteria blooms came back to or initiated in Skaneateles Lake in 2017. And we were working at Lake George with this, with kind of this new research paradigm, merging high frequency sensors and computer modeling, specifically of high resolution weather circulation. And we were directed, in quotes, to we were very much appreciated it, to come to Skaneateles Lake to hopefully provide some insights into what was generating the blooms. So we came and primarily, again, high-frequency sensors and computer modeling. That vertical profiler in the upper right there, that was the only sensor package that we had on the lake. And I want to point out to you, in that picture, there's some white streaks on the surface of the lake, and that's indicative of Langmuir circulation, which I'll talk about in a few minutes. This was the paper that came out of this effort, and highly recommend it. It's a long read, so grab a beer or a bottle of wine. And any questions you have that I can't answer, we obviously we can go back to the paper. As we go through this, I want to point out that the location of the vertical profiler, again, all of our sensors, were where that green dot is. And I believe that's pretty much in the vicinity of the water intake for the city of Syracuse. And that's actually why we were there. I didn't know that immediately at the time, but I understood that pretty quickly. And you'll notice that the positioning is in this upsloping trench, exactly what Chris was just showing us earlier. And it's we'll see that it's in kind of this wash zone of the thermocline. So I used to start at the beginning and end at the end, but everybody was asleep by that point. So now I start at the end, and then I work my way back a little bit. The crux of what we found, again, this is largely from the measurement data, but it was substantiated with our modeling data, was there was a three-step sequence that preceded every HAB on Skaneateles Lake in 2018. And there were a total of 8 confirmed HABs in that year. We deployed right at the end of July, and we were on the lake until the end of October. And the 8 HABs, they started right away after we showed up, which we caught a little flack from. But the first 3 were August 4th, 5th, and 7th. And then the last one, I think, was October 9th or 10th. But what we found was that they were all preceded by a disturbance of the lake bed by the thermocline. And I'll get into a little bit more detail on that in just a minute. And that then was followed by this vertical circulation within the water column. And that circulated, we believe, nutrients and cyanobacteria, basically on a conveyor belt through the water column. And both the thermocline raking the lake bed and the vertical mixing in the column were very, very wind dependent. The third step was the wind calming. And this is what everybody always associates with a precursor to a HAB is, well, things got very calm. And that's true, and that allows the buoyancy of the cyanobacteria to allow it to surface. So I'm talking about the thermocline raking the lake bed and then this vertical circulation. So just as a little refresher here, the thermocline rakes the lake bed as a result of internal waves. So that's a wave literally in the thermal structure of the lake. So you have warm epilimnitic water during the summertime, cold hypolimnitic water, and that boundary, which we're seeing as these lines in this diagram on the left, the line in the middle of the lake. That's the thermocline, and the wind deflects that, and when the wind stops, that can oscillate back and forth. And in extreme conditions, and in conditions that I think are very dependent on the depth of the stratification, this rocking back and forth, which is called an internal seiche, basically a standing wave, that can manifest as a progressive wave. So instead of the thermocline just rocking back and forth, raking the lake bed, it can turn into a singular wave or wave train with about an order of magnitude more energy when it shoals than does the internal seiche. So that's why we're talking about this raking of the lake bed. And it's in this area that Chris was talking about, this wash zone. Now on the right is Langmuir circulation. This is when you see the bubble streaks on the surface of the lake, more or less parallel with the wind. You're looking at the confluence of these helical coils of flow in the water column. That's Langmuir circulation. So this is data from the Brannan, Scholes, and Driscoll study that Chris was talking about, where as you go deeper in the lake, the phosphorus content in the sediment increases. And where, and that gray zone there is roughly what we calculated to be the wash zone of the thermocline raking the lake bed. So that's the depth region of concern, at least during our deployment in 2018. And we saw from Brannan et al. In 2023 that where our vertical profiler was, we were in a vicinity of something like 900 to 1200 ppm. So we were over a lake bed area that was very high in phosphorus concentration. This is data from early August. The top is wind speed and direction, time left to right. The heavy black bars are day delineations. The middle panel is a temperature profile, and the bottom panel is turbidity. And what the middle panel is showing us, and this is after, it starts on August 4th. This is after, on August 1st, I think it was, there was a 20-mile-an-hour wind out of the south for about the whole day. And so for that whole day, that wind was blowing the warm epilimnetic water northward, and it was deflecting the thermocline. And when that wind stopped on August 2nd, the thermocline started to oscillate back and forth. And so what we see in the temperature profile is this upwelling of the cold and blue in that, it's cold hypolimnetic water. Because of the geometry of Skaneateles Lake, the frequency of that is roughly every day. And this goes back to Marion's formula from the 1800s. The geometry of the lake basically makes it a clock, a one-day clock. It's just short of one day, but more or less every day that cold hypolimnetic water was upwelling, and then it was receding. With each upwelling, we see the turbidity at the lake bed bloom up. Now this is blooming up about 3 or 4 meters. So almost the height of this room. So the thermocline is raking the lake bed. It's causing this plume of turbidity off of the lake bed that we know is very high in phosphorus concentration. We also saw this this is ADCP data. It's the depth of the lake on the y-axis, time left to right. And what we're seeing, this is north-south velocity, we're seeing the receding of the water at the lake bed and then the immediate progression of it. And this suggests that our vertical profiler was deployed right at the south end of the wash zone as it existed for this time. So this is really the best example that we have of this three-step mechanism. We see at the 2 B's up there, we see internal waves coming through, that cold hypolimnetic water coming up. And at B prime, down at the second to bottom panel, so let me restart. Top panel is wind speed and direction. The second panel down is temperature profile. The third panel down is north-south velocity, I think. Fourth panel down is acoustic backscatter from the ADCP. And then we have turbidity, and then we have vertical velocity here on the bottom. So at B prime, we see the upwelling of the hypolimnion, both in the temperature and in the turbidity. But what happens is, if there's nothing to pull it upwards through the column, it just settles back down. So not every internal wave causes a bloom on Skaneateles Lake. What we see at F, the wind increases, and we start to see some Langmuir circulation going from D to D prime. Now you can see that in the vertical velocity. That's those those helical coils. And as they transit the vertical profiler, you see the lake water literally going up and down below your feet on the profiler. You don't really see that, but the instrument sees that. And we see at F, there's an intersection between the pluming lake bed, that turbidity, and the vertical mixing from the Langmuir circulation. And F is the magic. That's the magic, because that, subsequent to that, we start to see an increase in turbidity in the water column. So that's the mechanism I described with that first graphic. Now there's another mechanism that we describe in the paper as a shortcut. Now, what happens is when the wind from the south blows northward and it deflects the thermocline downward at the north end of the lake, it's setting up for an internal wave, but sometimes the wind can hold it there for a long period of time, hours to a day. The Langmuir circulation can go all the way to the lake bed, and that's called Langmuir supercells. We see that at I, and that's due to the wind increase up at G. So the wind increases at G. At H, it pushes that thermocline down. So we see the lake column, the column go isothermal at H. And if we trace down to I, we see the vertical mixing going all the way to the lake bed. And then subsequent to that, in the turbidity, we see the column getting very turbid. Now I want to zoom in here. So this is the same image, only I zoomed in, particularly with the acoustic backscatter, which is the fourth panel down. We still have the Langmuir supercells at D, and up at E, you can actually see from the backscatter, you can see lake bed material being entrained up. This isn't the first time this has been observed. This was really observed initially, I think, by Anne Gargette off the coast of New Jersey in about 2007, in, ironically, about the same depth of water. So we have these two mechanisms. Now, let's see if I can go back here. This is the previous diagram. I call this a week in the life of a HAB on Skaneateles Lake. This is 7 days. That last day, there's a couple of red dots in the middle of some of those panels. That was a confirmed HAB day. And you can see also in the backscatter, there's quite bright backscatter near the surface, and we believe that to be reflection, acoustic reflection, off of the aggregating cyanobacteria near the surface. So I included this because for years I've been talking about this kind of the shortcut mechanism. I finally put a diagram together. And this dovetails with what Chris was just describing. This is a crude depiction, by the way, of the north end of Skaneateles Lake. This kind of shallow 7-8 meter plateau at the north end, and then the deepening, which is this trench that we were over. When there's light to moderate wind, you can get Langmuir circulation, which is those vertical ovals that we have with the arrows on them. And at the north end of the lake, where it's only 7 or 8 meters, you can have Langmuir supercells. They probably happen all year long when it's breezy from the south. But the problem with it not creating a HAB every time that happens gets back to Chris's data and Charlie's data with the reduced level of phosphorus in that sediment in the shallower areas. But when that thermocline gets deflected, the way I have in the bottom panel, well, all of a sudden, that red depiction of Langmuir circulation, that's a new set of Langmuir supercells that now are penetrating to the lake bed in an area that we know has elevated phosphorus content. This is two images from our hydrodynamic modeling, and this just shows the top panel is more or less with the thermocline at rest. The way this is that the lake surface is kind of shown at an angle at the top with wind vectors. The tan-colored area is the epilimnion. The dark stripe is a 16-degree isotherm represented thermocline. And then the gray area is hypolimnetic water. And in the top graphic, we see basically a fairly relaxed thermocline. And in the bottom graphic, we see the deflection of, right here, deflection of the thermocline. And if anybody wants, I have some really great animations. I think I showed them back in 2020. This afternoon, we can certainly take a look at those animations, and it shows the dynamics going on in the thermocline, both during SACE events, i.e. kind of that rocking back and forth, and also progressive waves. So from that, we developed two predictive mechanisms, two predictive algorithms. This is basically only using three metrics. One is turbidity near the lake bed, the bottom 3.5 meters. The vertical velocity near the lake bed, again, bottom 3.5 meters. And then surface winds. So these represent the three main drivers that I talked about in that three-step sequence. And using empirically derived thresholds, we come up with this model. Now on the bottom, the gray bars indicate confirmed days with blooms, DEC confirmed. And the green dots are predictions based on this model. We do over-predict, but we're convinced that the lake was very likely set up for a surface bloom. It just never manifested as a surface aggregation. We also, now this is not in the paper, but we also looked at another mechanism to predict blooms. And here we're looking at, again, wind speed and direction, acoustic backscatter. I'll mention the third panel in a minute. This is as vertical velocity, and on the bottom is a summation of vertical velocity through the column. That third panel up from the bottom is looking at the variance of acoustic backscatter in the top 13 meters. The blue line is the instantaneous variance. The light blue line is a one-day moving average, and the dark blue line is a three-day moving average. And we noticed that when the one-day moving average went above the three-day moving average, it was indicative, again, the red dots in the next panel below are confirmed HAB days. So we call this the Habs cross. And what's going on here is we're only using acoustic backscatter. And we're saying, okay, well, when the variance is low, the backscatter produced by the cyanobacteria indicates that it's relatively distributed within a column. When the variance increases relative to the time leading up to then, it's very likely the cyanobacteria is starting to aggregate towards the surface. So we hit all four. We over-predicted on that second to last one, and we think that's because the lake was set up, but then there was sufficient wind to draw the cyanobacteria down into the water. By the way, in 2018, the cyanobacteria, it was there the whole time. This is, on the top is phycocyanin, instantaneous ½ meter down and 1 meter down. And then on the bottom is phycocyanin summed through, I think, the whole column. And I'll just mention on the bottom there, we can see that there's cyanobacteria in the column all season long. The red dots, again, are confirmed Habs days. I'll get back to the top in a minute, but one thing that's interesting on the bottom is that the first three Habs in August 4th, 5th, and 7th, they were during a relatively light region or area of time relative to the concentration of cyanobacteria in the column. So you don't need a lot in the lake in order to produce a surface aggregation. On the top is a detection mechanism that we developed, where again we're looking at 24-hour moving averages compared to the instantaneous. And it's a very simple algorithm. It's basically, well, when is the instantaneous some percentage above the 24-hour moving average? And I forget, something like 70% with one and 60% with the other. It's in the paper. But you can see we're detecting very closely all of the blooms that were confirmed. Now, I want to point out, if you remember where the vertical profiler was. It was essentially out in the middle of the lake, off of Mile Point, but so it wasn't in the middle of the lake, but it was halfway across the lake. And the confirmed blooms were scattered around the north end with one or two at the south end. And yet, out in the middle of the lake, we were still able to detect those blooms, even though they were confirmed on the shoreline. And the real takeaway for me there is that the blooms are not really localized. They're still being generated probably along this wash zone, out in the middle of the lake. And then they're just drifting in and out. And again, that cyanobacteria, it's in the lake. And what we call a bloom is nothing more than a surface aggregation that may or may not produce toxins. So, getting towards the end here, if anybody wants to try this at home, I keep harping on the vertical mixing, the Langmuir circulation. I think it's critical here. And that profiler in the upper left, that's on Skaneateles Lake. That's our Atlantis custom-built RPI and IBM. In 2018, again, you can see those white streaks. This was July 31st. I think it was a Tuesday. And that machine is what allowed us to create this beautiful ADCP data. But what we have found since then, we built a couple of new vertical profilers, and one of them is shown in the lower right there. The new profilers are bigger, and they have way bigger pontoons. Sounds great, except for those new profilers ride the waves. Now, when you really want to know about vertical mixing, it's when it's windy. And when it's windy, there's a lot of waves. And when there's a lot of waves, we find that the new profilers, they're so buoyant that they really heave quite a bit. And I'm having a very difficult time to generate this quality of data with these new profilers. There's just too much buoyancy to it. And so we're looking at ways to change the ping rate, which I'm almost maxed out with that, but also to kind of somehow put a shock absorber on the ADCPs. Now, I usually run long. How much time do I have, Steve? Because okay, I have some backup slides. I'll just go through these quickly. This is some bathymetric work that we're doing at Chautauqua Lake, which has been very helpful to identify this wash zone that Chris was talking about. This gets back to something Chris was mentioning. There's this constant thinking that, well, there's no internal loading going on in a lot of the Finger Lakes. In fact, this is the action plan for Skaneateles, and it says we don't think there's any internal loading. Well, I think that's, I think we know better at this point. So that's that. Another point I want to make, what the wind giveth, the wind taketh away. The wind and the calm wind generates these blooms, we think, and then it takes very little wind to generate a small vertical mixing at the surface to basically suck that bloom back down into the column. And the one thing I'll leave you with, so when we showed up on the July 30th of 2018, I spent most of the time deploying the vertical profiler and the rest of the time looking down into the water column in complete amazement of how clear it was. I mean, everybody had talked about how clear Skaneateles is, and I'm like, wow, they weren't kidding. Well, I had to come back on that Friday after this big wind event, but the day before the bloom, the first bloom on August 4th. And see if I can go back there. So that Friday, this is from the vertical profiler. I'm looking down, I'm seeing all this particulate. I kicked myself for not having filled a water bottle and looked at it under a microscope, but I didn't. My guess is that these are colonies of microcystis developing in the column, and this was the day before, It was extremely calm on the 4th, and then those colonies rose to the surface. And in fact, I got a call that day when I was out on the VP. A couple came up to me in a whaler, and they said, "Oh, this is great, blah, blah, blah," and I gave them a card. Well, they called me the next day, and they said, "Hey, we got stuff coming up on the surface. You guys know about this?" And I'm like, well, that was the start of us hopefully figuring out the problem. So let me go back because I need to leave it on. This. So I consider myself, I'm really the messenger. There was so much effort and work put behind this by a whole lot of people. I just feel lucky that I was part of, helping to figure some of this out, and that I get to come and talk about it to great people like you. Thank you very much.
Mark, that was a fascinating talk. Thank you. I'm Rick Smith, Global Aquatic Research. I was super interested in this because we see this often when you have HAB reports in shallow areas. We're out in the middle of the lake and we basically see them in various streams and pools kind of, occupying some percentage of the lake.
Yeah.
And something I know that came from John Halfman's work with FLI, they talk a lot about this nearshore loading of nutrients. And something they talk a lot about is macrophyte breakdown. So this is really interesting because this is probably a higher quantity of phosphorus overall, because you're talking about all the nearshore, basically these hot zone type areas, right, where you get deep enough that you have high concentrations of phosphorus in the sediment, but shallow enough that you can basically get these Langmuir supercells actually hitting the bottom, right?
Yeah.
If you look towards any kind of mass balance, is that possible to get from your data, where we can actually look at TSS, concentration of phosphorus, and then actually look at phosphorus requirements of the microcystis and get some estimates of biomass in the water column to see what percentage of their total phosphorus requirement, basically?
Yeah, I would say not from the data that we have. I think that would require an extension of the hydrodynamic model to really model it basin-wide. Because as much as I'm describing it as being kind of this homogeneous issue at the north end, there really is a lot of heterogeneity throughout the basin. So I think that's possible, not with the data that we have, but I think, building on that probably would be helpful. I want to bring up one other point. I mentioned when I showed the confirmed HABs, there was on September 13th and 16th, I think, there were blooms reported at the south end. Or near the south end, or actually about halfway up the lake. And that is kind of inconsistent with this model that I'm showing here. But what happened prior to that HAB event was a very energetic progressive wave. So what happened was the wind was very strong and it blew towards the north, and I believe the stratification had deepened. It deflected the thermocline, and when the wind stopped, there was such a mass of warm epilymnetic water that when it flowed back to even out, it actually depresses the south end, and this is textbook. It depresses the south end, and then that becomes a progressive wave. So it doesn't do this. It deflects so much that all the energy starts at the south end, comes up the north. And it's a depressive progressive wave, meaning there's this V shape to it. And because it's deeper and it's higher energy, it starts to nail all of the shelves up along the side of the lake. And that's when we saw this widespread bloom. And I'm happy to show you the animation, because we have that in our animation, of this progressive wave coming up and hammering all the shoreline, and then breaking at the north end. And this is another interesting point, and it complicates things. The progressive waves, if you look at the standing wave, it's like this, and you can calculate that wash zone. That when those progressive waves come and they have that depressive V or U to them, they shoal much further south than the Seiche wave. interacts with the sediment, but with much higher energy. So we didn't see those directly other than in our model, but we saw in our measurement data the after effects of this thing shoaling in the shallower, or in the deeper water. So it's shoaling in the deeper water in a whole different wash zone, if you will, or at least an extension of the wash zone. So I know that's not answering your question, but it is really kind of an interesting, a complicating factor of the whole thing. So on the one hand, I'm painting this as a simple picture, but as we all know, nothing's really simple.
No, thanks, Mark. That actually answered my second question. Are all these zones in play around the lake or just the north and south end?
Yeah, no, and this is where Chris's bathymetry really is going to be super valuable. And because I think that, if we can continue on with any of this modeling, we can start to see how that thermocline is transitioning around the lake and what areas of the lake bed are being impacted by it.
Thank you.
Thank you.
All right, we'll end there. Definitely time for discussion.
Great, thank you very much.
Okay, next up we have Dr. Bahram Salehi from SUNY ESF. And just a reminder for folks that are online, if you'd like to ask questions, feel free to use the chat option if you want to put a question in.
All right, good morning, everybody. I'm hoping with the help of this stopwatch and Steve's sign, I can keep being on time. So thank you so much to the Skaneateles Lake Association and the partners who helped organize this event. My talk is above the sea surface. Most of the talk we heard today, fascinating talks, mostly about the bottom of the lake. But I'm going to talk a little bit about the top of the lake. This work is not been possible without the help of my research assistant and PhD student. The two of them are here. Sajjad, if you want to raise up your hands, and Sina as well here, plus a bunch of other folks that are in this room that I will acknowledge at the end of these presentations. This image that you see, it is acquired or collected on September 18, 2000, or this year, by an airplane, a hyperspectral airplane from DRDC Canada, equipped with an hyperspectral sensor from Norway on an altitude of about 10,000 feet. So you can see a lot of interesting stuff on the lake. And then to be honest, I should say that this year was not the best year for remote sensing of HABs because the weather was, the situation was good, water was clear, and the Skaneateles Lake is a oligographic lake, which really does not work well with remote sensing stuff. We need to have a little bit of pollution in the lake to remote sensing, but we're lucky enough that we have probably the cleanest lake. So, but anyways, we tried our best to, conduct a campaign of multiple organizations helping us in here with drone, satellite, airplane, boat, and labs to synthesize all this data together to understand a little bit about the formation of HABs in this beautiful lake. So I'm going to have a quick introduction of the project, and then moving to field and satellite data collection. Field data, including water turbidity and chlorophyll A analysis. Then moving to machine learning algorithm that have been developed based on field data to monitor the lake. And then finally, using the developed machine learning, we're going to apply them to the entire lake to map the chlorophyll A and turbidity maps of the Skaneateles Lake on multiple days in 2025, and this is really an ongoing work. Like I said, the hyperspectral data is a very, very unique data set that have been collected over this lake, and then we have not gotten the chance to process them yet. So that's part of the big agenda for our ongoing research. So this is really a quick snapshot of the field work that I should say field and air work that we have done, collected over the past few months. These pictures are all taken in summer 2025, just last year. We see that it's a collection of satellite, aircraft, and boat. We have made sure to have concurrent acquisition of all these data together. You know, the satellites, such as Sentinel and Landsat, fly over our lake or our region at about 11:50 local time. And it takes probably 50 seconds for the satellite to pass over the lake. So that means that we have to make sure that we are all equipped and on the lake during that session. Obviously, the field data cannot be collected in 50 seconds, but we normally go to the lake with the research boat, with the support of Skaneateles Lake, the Bob, the research boat, really nice research boat, to be on the lake probably at about 11 to 3 p.m., 4 p.m., or 10 to 2 p.m., 3 p.m.-ish, to collect some 50 points across the lake, concurrent, you know, having the satellites over at one of these points. Then also we see that these airplanes, like I said, this is the DRDC airplanes right here, that equipped with the hyperspectral sensor, flown over 10,000 feet, both on Skaneateles Lake and Canandaigua Lake. So the Skaneateles Lake was 18th of September, and Canandaigua Lake was 16th of September. We collected some really nice data sets. We have got some drone data. We have been part of a international data collection campaign. It's called ROCKX, organized by Rochester Institute of Technology. I was the PI for the water quality, but there was a bunch of some 50 organizations from other aspects of remote sensing, such as nighttime or debris monitoring and other stuff in the lake. We got this chance to have been involved in that, and these data sets would be internationally available to the researcher across the world. Moving toward the objective of the work. So you may wonder how remote sensing can help, water quality. Well, many of the research that we saw or we see day to day is based on real world field data collections. But field data are limited. You can go just so many points a year or a day, and it's very costly. Remote sensing is here to help us basically connect the dots between the field and satellite signals. So we are trying to build a model, what we call it machine learning model, that build basically the relationship with the satellite, the spectral signature, with the field data. We train the model that the spectral signature of these satellite data are related to this much of turbidity or chlorophyll A that has been collected, the same position and the same point on the lake, and then build the machine learning model. So once the machine learning model is built and validated, of course, then it can be applied regardless of field work. So in any day in future, we can generate the turbidity and chlorophyll A in this case, and many other parameters of water, independent of the field day, and more importantly for the entire lake. So it's a wall-to-wall turbidity map or chlorophyll A map with a spatial resolution of few meters from across the lake. That could support a lot of research, such as the one that Dr. Mike and Dr. Chris mentioned earlier, that can be support of those. And then the ultimate goal is if we put together all this time series of this behavior of the chlorophyll A and turbidity over time, we can start seeing the behavior of the water and water parameter changes, hoping to lead us to some general conclusion about the formation of or prediction of the HAP. So that's the ultimate goal of remote sensing. So we are going to look at the past and current, and then moving to predict the future. That's the goal. So, but of course, remote sensing without field data is not, the starting point is field data. The field data that we have collected over Skaneateles Lake, it's some 50 waypoints across the lake. We start from north of side of the lake on the east or on the west coast, all the way point 1, 2, 3, all the way to point 27, and then go back on the east side of the lake. So these are the waypoints that we have been collected every time, same points, on the days that satellite data is available. So another thing that I want to mention about the satellite is satellite data. The availability of satellite data is one thing, then the non-availability of cloud is another thing. So we need to make sure that the satellite is flying over, but the cloud is not there. Plus, the wind is not there. So putting all these constraints together, make it very limited days for basically coordination of field data. But we have been lucky enough to work with a bunch of professionals that are, in the seconds of, the satellite data is flying. Well, we already know the satellite data, but the cloud is not really heavy today. Can we go tomorrow morning? Frank say, yes. So that's really the agility that we need to do this. So in this picture, you can see that, for example, this point 28 is collected at exactly the same time that the satellite has been passed over. And this is the shadow, the ghost things that you see, it's the bob that it appears in the satellite image. Well, the satellite image resolution is about 10 meters, and it's flying about 500 miles above the Earth. So it's not really high resolution, these type of freely available imagery. So before moving forward to the analysis, I'm just going to present some of the analysis of the field data, regardless of the satellite, that we have collected over these 4 major days. So these 4 days are the days that we went to the lake, collected 50 points. Well, the people, students and other personnel on 22nd of August, 3rd of November, September, 27th of August, and 18th of September. You can see that really, so this is a chlorophyll A, total chlorophyll A microgram per liter. It's really, really minor. It's pretty small, about 2 meters or 2 microgram per liter. We have a little spike here that likely is because of the nearness to the shore, which could be adjacency effect, reflection from the adjacent vegetation, because this is a point 27, and 27 is right here, is very, very end of the bottom of the lake. So that's one of the points that probably is not representative of the chlorophyll A. And on August 27, you see a slight change or increase in chlorophyll A, not serious in terms of the HAB, but you see that the trend is more or less homogeneous across the lake. On September the 3rd, a little bit more homogeneous, meaning that probably that day has been less windy days. And then moving to 18th, when the day that we have the airplane flying over the lake, we had more of variation in chlorophyll A across the lake, from point 2 all the way to more toward the middle of the lake. So that's indicative of a little bit of wind or changes of variation of chlorophyll A for other reasons in the lake. Then this is the turbidity profiles of the 4 days. Again, turbidity follow the same patterns. We have less turbidity in August 22nd, then a little bit more turbidity in August 27th, then a little bit more on September 3rd, and a different variation which is similar to trends of chlorophyll A. These two measurements are independent, so you can see that chlorophyll A and turbidity on the August or on September 18 has more variation in the lake. But these are just for the 50 points on the lake. We use these points to train or the AI models here. This is a little bit of summary of the data of field data. Again, this box, the lighter box shows chlorophyll A. The chlorophyll A has a sort of a general trends of increasing all the way to August 27, and then decreasing a little bit to September 3rd, and then again a little bit increasing on September 18. But they are within a very low range, which is not indicative of HAB at all, and that confirmed with other measurement in the field as well. And turbidity, also this is the trend of turbidity. Basically, these two shouldn't be on the same page because the units are different, but we normalized the units and showed it here. So, and then interestingly, we also collected water temperature. So water temperature basically drops, of course, throughout the season from summer to fall, from late summer to early fall, and air temperature increases in this way. Interestingly, we had a pretty cold day on August 27th, but water temperature remained high. So these are just the analysis that to understand the trends of water quality with regard to the field data. Another slide, we wanted to see the correlation between turbidity and chlorophyll A. It's pretty nice correlation, about 70% of Pearson correlation between these two indices, so meaning that the more turbidity, the more, oops, I have to, I guess, move much faster now. The more turbidity, the more chlorophyll A, and also the water temperature has an interesting relationship with chlorophyll A. Moving toward the satellite image processing, so we have raw data of the satellite, that's what you look from Google Earth probably, but the satellite data are contaminated with the atmospheric effect. This is after atmospheric corrections for the different dates, and this is a pretty cloudy day, but most of the lake is pretty basically non-cloudy. And this is the spectral signature of the water. As you see, we have a pretty homogeneous spectral signature of water on August 22nd, but we have pretty diverse spectral signature of that relate to the chlorophyll A and turbidity variation as well, so that's good indication. Another effect of satellite is the adjacency effect, meaning that in the shallower part of the lake, where the lake is adjacent to the shoreline, the spectral signature from the water that comes to the satellite is not coming directly from water, but it's reflected from vegetation to the water and go back to the satellite. That means the color really not representative of the water spectral signature, but the adjacent vegetation. This have been hugely affecting lakes, narrow lakes like this one. We have corrected this through an algorithm called Ecolite, and these are the area that has been contaminated, and this is the clear image. After all this pre-processing, we come to the developing of machine learning algorithm. We have tested a bunch of machine learning algorithms, such as linear regression and gradient boosting. We found that linear regression, in this case, pretty good result with R-squared value of 90%. That's mostly because we have limited data and nice data sets, as opposed to previous data sets that we have been used have been not basically co-registered with the satellite. Remember that these data have been collected the same day of the satellite, so that's a pretty nice correlation. Once the satellite is trained, we use, and this is for turbidity as well, so turbidity model, also we use the regression model, and then once this model is developed, it has been applied to the entire lakes for different lakes. So this is the chlorophyll A maps of the entire lake on each date. Basically, we use those 50 points, train the model, and apply the model on different dates. This is the behavior of the maps of chlorophyll A. This is another map for October and November. Also, we see pretty low turbidity, especially in November. It's very, very low turbidity for chlorophyll A. Similar trends. You can see that the average of chlorophyll A remains within below 2 microgram per liter, and then this is even way more less from September. It has been the maximum in September 19th actually. And this one is turbidity, the same map for the entire lakes. Turbidity again for the 5 dates that we have been discussing. And again, the trend of the turbidity, you can see there's a lot of information can be collected through this and being used for processing. And finally, this is the hyperspectral imagery that I mentioned. This is the hyperspectral one. It's not one shot, it is about 1.5 hours of imagery flight over the lake, because these are probably 3 terabytes of data sets. But this is just a snapshot, and here is just a digital elevation model of the lake. Chris showed a nicer version of this using LiDAR, but that's one is available publicly. And I just wanted to, again, we have not processed this hyperspectral data just yet, but some snapshot of different part of the lake. This is the hyperspectral imagery over 10,000 feet above the lake from, I believe this is the Country Club. And then you can see all these sediments loading or all this colorizing in here. It's only 3 bands, but with hyperspectral sensor, we have over 500 spectral bands, meaning that we can process and get a lot of information by analyzing these signatures. Here is the signature of the hyperspectral signature. In this case, it's near infrared bands, about 200 bands of hyperspectral signature. Again, that's going to be an ongoing research in the next few months. And I want to thank all the sponsors and collaborators of this research. Would have not been possible without all the help from the sponsors and the student and the staff involved in this research. Thank you so much.
So we have one question in the chat. It says, do the thermoclines circulate in the entire water column such that the oldest water is brought to the upper layers and thus circulated through the Syracuse intakes? Or is the water at the greatest depths as old as the lake itself, or trapped over a long period of time, I guess, is the question.
I believe this question is either for Mike or Chris. I didn't take care of the bottom of the lake.
So does the water stay at the bottom over years and eons, or does it keep moving around?
Well, according to Professor Driscoll, there's a full turnover in the fall and spring.
Want me to say? I can do that. So
You got
over the course of the season, the lake will stratify, so the upper water will basically won't mix that much and the lower waters won't. But then basically at the end of the season, you'll have a full turnover and you'll have complete mixing. So within the season, it's sort of mostly the same water, but then across seasons, there is relatively complete mixing. Okay, so we'll take a break, 7 or 8 minutes, and we'll be back.
Is this off? Another announcement for folks online. As a reminder, if you are using the chat, make sure you send to both hosts and panelists so we can monitor your questions. And feel free to use the Q&A as well. Both will work. Thank you.
So we good? All right. Just a 2-minute warning and then head on back. We'll keep things on schedule.
Okay, I think we're going to get started now. Can you hear me? Can you hear me? Okay, I think we're going to get started with the next speaker. No, I'm good. But we got a lot of people back there. All right, we're going to get started here with the next part of the program. So I'm going to talk about a little bit of paleolimnological work that we initiated a few years ago, and it's just really coming to fruition. This is part of the dissertation of Mackenzie Brahman, who is starting assistant professor at University of Kentucky. So I'm going to present some of her work, but it involves Chris Schultz and also Melissa Chipman. And so what this is to try to look at sort of the historical changes in both the nutrient and a little bit on trace metal chemistry in lakes. It's really part of a study that we looked across 2 lakes, Oneida Lake and Skaneateles Lake. I'm not going to talk about the Oneida Lake work, just focusing on Skaneateles. We just submitted the paper in responding to some comments. So if anybody's interested in this, let us know and we can give you a copy. So the focus is on Skaneateles Lake. We collected sediment cores to look at changes in the processing of materials over time at cores collected in the north part of the lake and the southern part of the lake. So you're all experts on the lake. You know that it's a relatively deep lake. It has a very small watershed relative to the lake surface, and it's obviously a highly oligotrophic lake. So these show you some photos, or not really photos, but images from Chris earlier about the nature of the sediment materials for the cores that were collected at the north end of the lake and the south end of the lake, and try to emphasize some of the characteristics that Chris talked about earlier, that the southern end of the lake, relatively undeveloped, relatively steep slopes, because we'll see different patterns in terms of the north and south end of the lake. Also a little bit about the drainage basins coming in. So particularly in the south end of the lake, there's some large tributaries, Grout Brook and Bear Swamp, and the north end of the lake impacted by Harold Brook and Shotwell Brook. Okay, so as I mentioned, this was done in 2022. We collected 4 cores, 2 in the north, 2 in the south. They were sectioned at half-centimeter intervals, dated using lead-210 and cesium, so we can assign dates through the depth of the cores, and then analyze these for a whole host of analytes, carbon, stable isotopes of carbon, nitrogen, major analytes, phosphorus, calcium, and I'm going to show you some of those. This is the dating work that was done by Melissa Chipman, who's unfortunately left SU. She's now down at William and Mary. So this is the northern core and the southern core. This is the date that's assigned, and you can see the depth of the lake from the surface of the sediment down to the depth, and the assignment of the date. So you can see this extends the record over a couple hundred years. So it's really a long-term perspective. Part of the motivation for the study was really to try to look at the long-term changes that have happened in the lake. And some of you remember the 9-element plan that was mentioned earlier in the presentation. It's to try to put that present-day ideas about what's happening in the lake in terms of this long-term perspective. So one of the things I'm going to harp on is this piece right here, which is the mass accumulation rate. That represents the rate at a given point in time of the deposition of mass into the sediments that have accumulated within the sediments. And so if we start out in the southern core, that's right here, you can see that the mass accumulation rate back in the day was relatively low. Oops, sorry. Oh. And it's increased over time. A little bit unexpected for us is for the northern end of the lake, which it started out low, and then it increased over time, and then starting about 1970, we see a decrease in the mass accumulation rate. So it's a little bit unexpected. Okay, so this, it's a little bit complicated, but what you're seeing here is on the left-hand side, the northern core, on the right-hand side, the southern core, and a series of analytes, and they're all oriented by the lead-210 dating. So this is earlier on, around the 1800s, and this is up to modern. And so you can see a number of materials. So we measure the concentration of these analytes, and we also take the mass accumulation rate times the concentration to look at the deposition or accumulation of these materials. So there's 2 drivers of the patterns that we see: the concentration in the material that's depositing plus the mass of material. So but that's important to keep in mind in terms of the overall presentation. So if we can focus on what I showed you previously, the mass accumulation rate, you can see here for the southern core, back in the day, relatively low rates, and then starting around the 1900s, large accumulations. Now, Chris and I argue about this. I view this as being very spiky, a lot of variation in the accumulation rate, which I attribute to the topography. He poo-poos me a little bit, so we go back and forth on this. If we go to the northern site, you can see again it is low, starts increasing in the early 1900s, increases, and then reaches a peak around 1970, and has actually dropped rather substantially in the most recent years. And so this reflects the long-term settlement of this area, okay? So this area was populated, except for indigenous communities, a long time ago. After the Revolutionary War, it was deforested, a lot of agricultural activity, and that has fallen out to some extent. It's less prevalent than it was, and so we can see some changes over time in that. So as I mentioned, the increase or the decrease in the sediment accumulation rate that we see in recent years is a bit of a head scratcher. We've been sort of quizzing Rich Abbott to see if he can give us some insights in why this is, but it's a good outcome. it's a good outcome that the mass accumulation is decreasing, at least in the northern core. And it's consistent with some coring that we did in the early 2000s, so that is useful information. Okay, so if we look at the phosphorus that most people are interested in, let me start at the south. The phosphorus concentration relatively low, and then you can see, although it's fairly spiky, increasing over time. And then the concentration in the northern core shows a similar pattern, relatively low in the 1800s, and then starting in the 1900s, increasing. A lot of variation over time, but an overall long-term increase. If we take the concentration of phosphorus and multiply it times the mass accumulation rate, we get the mass accumulation of phosphorus. And so you can see here for the southern core, that's right here, you can see it's low and then it increases over time. And the northern core reflects a slightly different pattern. It's low, it increases around 1900, and then you could say maybe it reaches a peak, maybe it's decreasing a little bit. And there are two drivers of this that are opposing. One is that the mass accumulation rate is decreasing, but the concentration is increasing, okay? And then, lead 210 dating, okay? But I'll do questions at the end if I get time. And then an interesting pattern that we're quite interested in that was mentioned previously is calcium. We see an increase in calcium, which is reflective of increases in calcium carbonate deposition, and this is a reflection of increases in productivity plus a warming of the lake, resulting in precipitation of calcium carbonate from the water column. So these are a few other analytes that give us insight in terms of the sources of material in the sediments. Again, the south and the north. On the far right-hand side is total organic carbon, and then stable isotopes of carbon, C13, and then the carbon to nitrogen ratio. These are reflective of materials. You see the total organic carbon concentration for both cores is relatively high back in the day in the 1800s. Decreases to a minimum value when agriculture was peak in the late 1800s, early 1900s, and has been increasing back up, coinciding with maybe this reforestation. If we look at the components of carbon, particularly the carbon to nitrogen ratio, the values are relatively low, which are suggestive of the importance of in-lake materials in supplying carbon, so macrophytes and algae and materials like that. People look at the carbon isotopes and the carbon to nitrogen ratio to try to sort out external sources from land plants versus algae in terms of sources of carbon for the material, for the sediments. So one thing we tried to do to put this all together is we did a statistical analysis known as a principal components analysis, and we found two aspects of the first principal component. Mass accumulation rate and phosphorus accumulation rate strongly drive major changes. So a more negative principal component indicates a stronger input of mass accumulation and phosphorus accumulation. And you can see the patterns, the differential patterns for the core 1, which is in the north, and core 2, which is in the south. So you can see it was highly positive at lower mass accumulation rates, and then you can see a transition around the middle part of the 1900s, which has continued today. The northern core, slightly different pattern. For most of the record, showed a similar pattern. And then around 1970, it's switched a little bit, suggesting some recovery driven by decreases in the mass accumulation rate. So a little bit conclusions on this first part dealing with nutrients. We see increases in mass accumulation rate from the most early part of the records, which are consistent with settlement and agriculture. The patterns of organic carbon and carbon to nitrogen ratios suggest that the source of the carbon to the system is largely from internal biological activity, macrophytes, and algae. And then we see these changes in the northern core, that we see a decrease in mass accumulation rate that's occurring, which is interesting, and we're not sure. It's presumably due to actions to reduce the sediment loading to the northern part of the lake, some of the activities by the city of Syracuse and others, the county, to try to reduce that mass loading. So we see that there is this long-term increase in phosphorus concentrations, rather large increases, and it's due to two factors. One, increases in the phosphorus content of the sedimenting materials, and two, an increase in the mass of that sedimenting material. So both go and increase the phosphorus loading to the sediments of the lake. So the other thing I want to talk about, if I have a second or two, is something that some of you know that I'm particularly interested in, that's trace metals. So in addition to nutrients on these cores, we measured a number of trace metals, and I just want to focus on two elements of interest. One, maybe nobody except for me is interested in that, and that's mercury. And the second is copper, and copper has been of interest because of copper sulfate treatment and suggestions that we might do copper sulfate treatments as a control on harmful algal blooms. So these are a series of cores like I showed you before for phosphorus, but what I have here, again for the south and the north, is I've got the mass accumulation rate on the left-hand side, and then the concentration of mercury, the concentration on copper, and then the mass flux of mercury and the mass flux of copper. So what we see here is we see that in the recent sediments, we see increases in the concentration and the mass flux of both copper and mercury. Mercury is largely associated with atmospheric deposition. Mercury is an air pollutant from coal combustion, mining activities, and things like that. And so it's an important contaminant for these systems. We do see some evidence in some of these cores. You see in the northern end that it looks like that there might be some decreases in recent years, and that's consistent with controls on mercury emissions in the United States. So if we look at this, we can use zirconium as a tracer of internal sources of mercury versus external sources, and we find that most of the mercury coming into the system is from outside sources, presumably atmospheric deposition. Steve told me I've got to move this along, so a little bit on copper. So copper sulfate was applied starting in the 20s to 1970. It's shown here on the copper slides for the north and the south of the period, and you can see where that copper was added. Not surprisingly, we see large increases in copper concentration and accumulation in sediments, and we see some decreases in recent years. However, the surface concentrations are still quite a bit higher than background concentrations. Okay, so just a couple of quick conclusions on trace metals. We see increases over the record of several hundred years of increases in mercury, consistent with atmospheric mercury deposition, and some evidence of diminishing values in recent years, which are consistent with reductions in emissions. And then we see some increases in copper, which are consistent with the application of copper sulfate, and again, some decreases in recent years. So if I've got time, I'll take a question or two. Thank you for your attention. You gonna let me off easy? Yeah?
A little bit about the data history, historical data. It's very amazing that you got data from 1800. You comment on that? I'm sorry.
Okay, yes. So what we do is we collect sediment cores into the lake down for some distance, and we section them in half-centimeter intervals. And then we date those for lead-210. And with the decay for lead, at the decay rate, we can date the individual according to values going back maybe 250 years, something like that, relatively accurately. So it's for semi-near term over the last couple centuries. And so then we can apply for each of those half-centimeter intervals, we can designate a lead-210 date. And then we measure the chemical constituents, and we know the mass accumulation rate, and then we can determine the deposition rate. Yeah. And so we can look at how the lake has changed over a longer period of time and what were the conditions back really before a lot of human development and how it's evolved over time. So it helps us put the 9-element plan in perspective. No, because the lead-210 dating is limited by the decay rate. And so really, I mean, Chris is the expert. What would you say, 200, 250 years, something like that? Yeah. So that's really pressing it, yeah. Okay. One quick question. Do I have time, Steve?
Thanks for your presentation, Charlie. I'm curious, do you have any theories about the differences in observations between the north and south cores in recent years?
Yeah, that's a good question. So I think it's the northern end of the lake is much greater developed, a lot of ag activity, where the southern part largely forested, also very steep slopes. So characteristics of probably episodic events. So there's a variety of factors happening. There's land use change. There's also climate change, which is influencing the hydrologic regime. So I think that those are big drivers between the differences between the north and south end. I mean, a key question is what's driving the decrease in mass accumulation rate. That's really great news in terms of the phosphorus loading. So if we could really understand what the primary driver of that is, that we could try to do more of that and try to limit the mass accumulation rate. So thank you very much.
Okay, next up we have Dominique Dominio from ESF.
Hey everyone. So today I'm going to be talking to you about a 50-year data set, and thankfully the city of Syracuse has provided me with this data. So I'm going to start a little bit about algae and what algae is, move on to objectives, talk a little bit about the methods, going to results, and then the overall takeaway for what has happened in the past 50 years. So what is algae? Algae is a microscopic organism that uses sunlight. But unlike when I say animals or plants, which are both monophyletic, so for animals over here, every single animal that you can think of, whether it be a bee and a wasp or a human, falls under this one category. For every plant, it falls under that one category. When I say algae, everything else that is highlighted is considered an algae. So some are very similar to land plants because they're a part of the same tree. Some, like cyanobacteria, fall under the bacterial domain, and then everything else falls under other domains. So when I say algae, it's not just one thing. It's very, very broad. So here are a few of the most common species over the past 50 years that have been seen, where we have Skaneateles up in the right corner. We have Skaneateles. Both of these are diatoms and made of glass. We have a green algae right here, Cosmarium. We have Dinobaran, which is my personal favorite, which is a golden algae. And then we have Skaneateles, which is a cyanobacteria. And so even though they're all parts of the phylogenetic tree, we consider all of these algae. And so when we're measuring chlorophyll, all of these will be measured as one thing. But they are all very different. So with that little bit of background, we're going to talk about what factors have changed over the past 50 years. Then hopefully we can look at some long-term algal trends in Skaneateles Lake. And then finally, does any of this actually provide insight on what happened and why a bloom occurred in 2017 and more recently? So first of all, we're going to go back even farther in time. We're going back into the 1920s. There was a paper by Jackson and Meyer written in 1966 that looked at data from the early 20s and then 40 to 64s, where they measured at 8 locations across Skaneateles Lake. And this is all at 6 meters in depth. In the paper, they discussed that there was a paper published in 1914 saying that the majority of algae fell within the 5 to 10 meter range, and so that's why they picked that 6 meter depth range. And they collected the water, looked at it underneath this Sedgwick rafter chamber, and this chamber basically has little grid marks where you can more easily count the algae cells as well as determine what genus they are. And so this is a very common cell technique to differentiate what algae and how many algae there are in the water column at the time. So now moving on to the City of Syracuse data set that I think it was 3 interns from the City of Syracuse took sheets that look like this that were in files and turned it digital this summer. And then they handed off all that data to me. So this data is from 1973 and then 1976 to 2024. And they used the exact same methods in that time period where they had the same 8 locations at 6 meters depth. And approximately 10 times a year, somebody went out, sampled the water column at these 8 locations, but they did add one other thing on top of it. They wanted to measure temperature as well to see what was happening in the water column at the time. But there is one caveat that I want to mention. In June 1992, they ended up taking a stage micrometer and looked at it under the microscope, and they realized they were underestimating the amount of cells that they were counting because they were trying to get the cells per milliliter. And so anything before 1992, it actually was underestimating the amount of algae they were counting at that time. So just a very quick overview. Most of you had much prettier bathymetric maps than me, but here we can see that Station 1 was in very, very shallow water. Station 2 was a little bit deeper, and stations 3 through 7 were in very deep water, and then Station 8 was also, again, in much more shallow water. So for the first objective, what are factors that have changed over the past 50 years? And I'm only focusing on water temperature and invasive species today. So first of all, the water temperatures over the past 50 years, you can see that over time, the water temperature has increased. And by just looking at this data, it doesn't give us the full story. So I wanted to look at it in a couple different ways. So firstly, how many days was the water above 15 degrees Celsius? And the reason why we're looking at 15 degrees Celsius is because if the water is warmer than that, you're more likely to see a higher amount of algal growth. In the 80s and 70s and 80s, you generally had between about 100 to 150 days that were above 15 degrees Celsius. But as you can see, as time went on, there were more and more days lengthening the growing season of algae in the water column. So the last few years, we have actually had more than 150, closer to 200 days where algae can grow, indicating that maybe more algae can grow in the water column. But it's not just the minimum temperatures, it's also the maximum temperatures are also increasing. So in the 80s, you generally had around 10 degrees Celsius in the water column in that May-June timeframe, but now it's actually closer to about 15 degrees Celsius in that May-June timeframe. For the maximum temperature, during midsummer, where we have that August, late July timeframe, it was around 22 to 23 degrees Celsius on average, but now it's closer to 25. So with this, we're seeing warmer temperatures, not just in the early spring, but also in the late summer and early fall. Moving on to the timeline of invasives, if anybody has any data to help me narrow down this timeline a little bit more, please let me know. I'm only going to be focusing on zebra mussels today and quagga mussels. And based off of the data that I have been able to find, zebra mussels entered into Skaneateles Lake somewhere between 1991 and 1993. And quagga mussels was around, I think it was 2008 to 2010 region. And I want to bring this up later on. So keep that in the back of your mind, these two timeframes. But as you can see, there were a lot of other things happening that were coming into Skaneateles Lake as well. So based off of what we just talked about with invasives and water temperature, let's look at this long-term algal population trends. One thing that, at least in my field for a really long time, we're always like, oh, warmer temperatures will lead to more algae, specifically more cyanobacteria growth, because cyanobacteria generally like warm waters. In Skaneateles, this does not seem to be the case, where if we're looking at just that post-1992 data, because I wanted to avoid that caveat that I mentioned earlier, the warmer temperatures did not necessarily mean more cyanobacteria growth. It did mean more algal growth, but not cyanobacteria specifically, which was surprising to me. So now we're looking at the relative percentages of the phyla, where we have blue for cyanobacteria or blue-green algae, and gray being the diatoms. Pre-1992, the majority of the water column had a lot of diatoms, and the majority of the algae that they counted under the microscope were diatoms, with a very, very small amount of cyanobacteria. As we move on, you can see that cyanobacteria started having a much higher concentration over time. But for the first part, it was actually this one genus, Skaneateles, where almost all of that concentration of cyanobacteria that was seen in the early part of the 90s to early part of 2000s was this one genus. And another little tiny caveat, Skaneateles is really small. Most of the time it's around 3 micrometers under the microscope, so it's really hard to see and really hard to identify depending on what microscope you're using. But what also happened at these two time spots? In somewhere around 92, zebra mussels most likely moved into Skaneateles Lake. And could this be why we're seeing a massive increase in cyanobacteria? And then with the quagga mussels coming in around 2008-ish, we're also seeing another spike in cyanobacteria. And when we saw on the last slide, that the cyanobacteria phyla also changed as well. So let's look at this in a little bit more detail. I'm sorry, these figures are kind of small. So we're looking at Denobrian right here and Cyanidra right here. Both of these are not eaten by zebra mussels or quagga mussels. So we would expect potentially these species to have a much larger concentration in the water column. But based off of these red lines right here, they're pretty flat, right? You're not really seeing much of an increase. So maybe the hypothesis that this is coming from zebra mussels might not be the case. But with these two figures, or these two species down here, Skaneateles and Cyclotella, zebra mussels and quagga mussels can also eat these. And we can see at the start of 92 to present, there actually has been a decrease in the concentration of Skaneateles cells, and the same pattern happened for Cyclotella. But this could also just be happenstance, and we're not really sure what this means. So right now, maybe some type of those mussel invasions are causing that shift in phyla in the water column. And here are the top species that have been seen in the water column over the last 30 years. And there have been over 120 seen since the early 70s. However, some of them, like Asterianella, Cyanidra, and Tabellaria, have been seen since the early 1900s. So the way you read this is the closer to green it is, the more cells there have been counted under the microscope. If it's yellow, that's a medium amount, and red means it's occasionally seen. If you just see it as white, that means those cells were not seen under the microscope during those time periods. So based on what we were just talking about, we have Cyanidra up here, which has been around for a really long time in Skaneateles, as well as these three genera here. But the one that I mentioned right here at the bottom, Cyanidra, or Skaneateles, was not seen in the water column until the early 90s. So this might be one of the genera that are newer to Skaneateles Lake, or because it's so tiny, microscopes might not have been able to pick it up depending on what microscope was being used at the time. So what does this mean as the population over time? So this is an NMDS plot, basically showing what is occurring for the population of algae over time. If we look at the red circle here, this red circle is indicative of that 73 to 82 timeframe. The orange is 83 to 91. And then over here, we see all three timeframes kind of overlapping, and all of those are after that 1992 timeframe. So we see a massive shift in phyla pre-1992 and post-1992 based on what was being observed underneath the microscope. But based on the stress level right here, it's actually showing that there is a population shift over time, and each time was actually significantly different than one another, even though it is overlapping, especially in the post-92 period. So finally, can this tell us anything about what's actually happening and why blooms are occurring in the lake? First, we have increased temperatures, which generally means more cyanobacteria. We have the potential invasion of mussels into the water column, as well as we have very consistent methodology from the early 1900s, for the most part. And we saw that shift in genera, and it's actually shifting to having a lot more cyanobacterial species. And there are higher temps, but these higher temps at the current moment are not leading to more cyanobacteria. Right now, Seneca cystis is the main genus. And one word that I haven't mentioned yet is microcystis. Microcystis was not really seen at this 6-meter depth range, at least in this algal population. So as of right now, this 50-year data set is not a good indication of why the blooms have been occurring in the first place. So with that, I want to thank Rich Abbott from the city of Syracuse, because he has been extremely helpful, as well as the nappies. With that, I'll take any questions if I have time.
I'm Phil Joy. Do you think there's any relationship to alewife change with the algae population?
So with the very little bit I know about alewife, I know that they can come in and take over some of the other fish populations, right? Is that true?
Yes, yeah, they displace the ciscos
Yes.
usually, and they tend to eat the larger Daphnia and the cladiphoras.
So with that, it's actually changing the population on the larger scales. And so that is so far upstream that based on this data, it's really hard to say anything, because you have to go through all the different foods that the fish eat, as well as the Daphnia and the cladophora and all those fun things.
So that would mean, did you look at the zooplankton any? No.
There is no data on zooplankton. They were looked at, but they were never written down, so I don't have that data.
Thank you.
Thank you.
Okay, next up we have Ryan Ruggiero, a PhD candidate at SUNY ESF.
Okay, good morning. So today I will be presenting my work on drivers of nutrient export from New York watersheds. So a common assumption is that land use and watershed characteristics control nutrient loading. And here we ask whether this relationship can be detected across many watersheds. Our objectives were twofold. First, we asked whether watersheds with more human land use export nutrients differently during runoff events. Second, we test whether describing watersheds in more detail improves our ability to predict nutrient export. And so here, detail refers to the spatial scale of land use, which I'll get into. So for the data, New York State watersheds with long-term nutrient and flow data were analyzed. Our focus was on 3 water quality constituents: total phosphorus, which is TP, and we had 55 sites. TN, total nitrogen, had 23 sites, and SRP, soluble reactive phosphorus, which had 50 sites. And this map is of New York State, and these were the sites that were used in the analysis. And the color, so the watersheds are the little polygons, and the color represents the data availability by constituent. And so these 3 constituents are important macronutrients that are linked to the harmful algal blooms, with SRP representing the fraction of TP that is immediately available for uptake by the algae. Land cover, soils, and slope information were used to generate watershed characteristics, including this term that I'm going to introduce now, which is presumed nutrient generating areas. So the nutrient data were aggregated into a single metric for each watershed. And so there were 3 metrics for each watershed: the nutrient export rate during storm events, the median concentration, and the annual average loading rate. So yeah, and then we fit multiple linear regression models to determine how well the watershed characteristics predicted these nutrient export metrics. And so like I've been talking about, land use was described at multiple spatial scales across the entire watershed, within the riparian zone, and in areas defined by the intersection of poorly drained soils and steep slopes. So this diagram with the yellow rectangle can be used to demonstrate the land use at the 3 spatial scales. So let the yellow polygon represent the entire watershed. The red polygon represents the riparian zone, and the gray arrows would be areas of poorly drained soils and steep slope in the watershed. So any human land use, so like agriculture or urban, that fell within these zones was divided by the total watershed area to calculate human land use at each spatial scale. And then on the right of the slide, there's 4 data layers. So there's elevation, soils, and land use, and hydrography. And these were the 4 data layers that allowed me to determine land use at these spatial scales. So nutrient export rate was quantified using the slope of the concentration discharge relationship in log space. So I have some plots showing, so on the left, the 3 plots show each pane shows concentration on the Y and discharge on the X. And so the first pane represents a positive slope, and this indicates that nutrients mobilize with increase in discharge. And this suggests that the nutrients are progressively dislodged from a nearly unlimited source during runoff events. And we call that mobilizing. On the right pane is a negative slope, and that indicates that nutrients come from a finite source, and thus they dilute as flow increases. And then the bottom pane is slopes that are not significantly different from zero. And this indicates that nutrients release at similar rates across the range of flows, which we call stationary. So to address this question of do watersheds with more human land use export nutrients differently during runoff events, we examine these C2 slopes as a function of human land use in the watershed. So for TP and TN, both developed and undeveloped watersheds exhibited a wide range of slopes from dilution to mobilization. So in contrast, for SRP, more developed watersheds generally showed mobilizing behavior, suggesting human land use promotes the release of immediately bioavailable phosphorus during runoff events. All right, so to test whether describing watersheds in more detail improves predictions of nutrient export, we built the multiple linear regression models using watershed characteristics like number of concentrated animal feeding operations alongside land use at the 3 spatial scales. So for simplicity, I'm just going to focus on the median concentration of SRP as the patterns were similar for the other constituents. So models using watershed scale land use explained as much or more variability than those using riparian or this PCSA scale. So this suggests that nutrient generating areas across the watershed are important, are as important as those adjacent to the stream. But one caveat could be that our stream network may not have captured all of the hydrologic variability. But this does suggest that it does capture most of it, as you know, these scatter plots look pretty similar. And then the poor performance at the PCSA scale does not mean that the intersection of land use with poorly drained soils and steep slopes is not important. It just suggests that restricting scale restricting the spatial scale of the land use means that we lack sufficient information to predict nutrient export at the aggregated level used here. So the aggregated level meaning we removed the temporal component, so we only had one metric, which was the median concentration for the watershed. So human land use did not correlate with nutrient mobilization as expected for TN and TP, although a trend was observed for SRP. Similarly, increased spatial complexity did not improve predictions of nutrient export metrics for any of the 3 constituents. Overall, these findings suggest that efforts may be better spent on improving the specificity of water quality monitoring rather than adding complexity to predictive models. In Skaneateles, this could involve more frequent edge of field monitoring to identify and validate the most important nutrient generating areas, along with the effectiveness of nutrient management practices. So future work will incorporate the temporal component of this statewide data set, enabling more thorough testing of the drivers of nutrient export. Flexible machine learning models, such as decision trees and artificial neural networks, will be evaluated to capture complex interactions among water quality, land use, and other covariates. So I appreciate your attention. This was funded by the DEC, and yeah, I'll take any questions.
Hi, Ryan. Chris Legg, Town of Skaneateles Supervisor. Thank you for the presentation. In talking about SRP, you cited CAFOs as one of the contributors. Correct me if I'm wrong, but septic systems are a significant potential source as well. And in your conclusion, you were talking about looking at sampling to include, I assume EDGE is talking about, for example, sampling specific tributaries to see what is coming into the lake through the surface and how that could relate to the use of the land.
Right. All right, so I'm detecting like two questions. One, like, is SRP potentially higher in the subsurface flow? It depends on the soil type. I mean, this is just from my experience, I could say that if the soil type has like a lot of large preferential flow pathways, then the SRP probably won't bind to the soil. So it will be a potential high transport mechanism. But normally phosphorus has an affinity for soil. So, I mean, I don't want to say the literature is changing, but I think the literature has trended towards if the water is going to move through the matrix of the soil, then you're not going to have a lot of soluble phosphorus. So that's why the CAFOs and the human land use, we saw a different signal for that for SRP mobilization, because those nutrients are applied directly in the pathway of surface runoff.
Okay, thanks, Ron.
Yes. Thank you.
Thanks, Ron.
Yes.
Okay, we'll take another 10-minute break or so.
Hi, Happy New Year. Great to see you. I'm doing well. I do love seeing that. I can sign and scan
No, it's good. And I'm always a little bit like, oh, is everything working?
Yeah, and I want to make sure I understand how to advance it.
Yeah.
So this thing works. Sorry.
And then actually, you can, yeah.
I'll probably use this.
And if you want to point at things, I think people have found there's the active cursor.
Yeah, I don't
That's-
think I will.
Okay, that's more visible. So if you find yourself just saying,
Yeah.
oh, this plot, I think that's better than the pointer. Pointer's
The pointer seems,
Yeah,
I've noticed that I couldn't see it
You
at
couldn't
all.
see it.
Yeah,
10 feet away.
but I think I'll just,
Okay. Yeah, seems to be working.
most of my slides are still.
So are you still doing I'm sure you're seeing that I got awesome together. Just give it 2 minutes for you. Okay. Hi, everyone. If you would start moving back to your seats, we'll get going in 2 minutes here.
We don't have any talks on that, but we have gene for one of the precursors. System. Yeah. I don't know how far back the waste. So we'll go back to so back to we don't have those data yet. Total but the gene data for Skaneateles doesn't show much retention until 75. Well, it's been a change. Yeah.
Okay, thanks everyone for headed right back. So we're ready to start our program again. So we're going to start off with Dr. Bob Howarth from Cornell University.
Thank you. Thank you. Thanks for the invitation to speak, and thank you all for coming today. I have a bunch of co-authors here, and I particularly want to acknowledge Tom Butler, who's in the audience over there, Dennis Swaney, Roxanne Marino as well. All of the field work I'm talking about today was done by Tom Butler, and most of the synthesis was done by Dennis Swaney, and I'm just the point person, the PR specialist, if you will. We also have some EPA colleagues, and you'll see how their work comes into this. So you've heard already from Charlie that the watershed for Skaneateles is small relative to the surface area of the lake, and it's very small and far smaller than any of the other Finger Lakes. And based on that alone and the fact that people have been trying to protect the watershed for some time, you'd expect that there'd be relatively low nutrient loading from the watershed, and I think that's true. That's why it's such an oligotrophic lake. But we're interested in the airshed, what's coming in through the atmosphere. And we're particularly looking at ammonia gas because it historically has been understudied, and we think it could be important, and I hope to convince you that that might be the case. The airshed, of course, is much larger than the watershed, and there's a lot of agricultural activity upwind of Skaneateles Lake, so the question we're posing, is that important as a nitrogen input to the lake? Now, I want to explain a little bit why we're interested in nitrogen. And I want to make it clear that we do not think that nitrogen is regulating the growth rate of phytoplankton, including the toxic cyanobacteria in the Finger Lakes. The Finger Lakes are all clearly phosphorus limited. We've known that for a long time. Just give me a couple of examples here. Bruce Peterson, PhD from Cornell in 1971, clearly showed that Cayuga Lake is phosphorus limited, and my student Brian Roberts, who got his PhD in 2004, showed that Skaneateles is phosphorus limited. You'd expect that. The inorganic N to P ratios are 1,000 to 1 or greater across all of the Finger Lakes. So why am I interested in nitrogen? And it's because we think nitrogen might play a role in the blooms, not by encouraging the growth of the organism, but by prolonging their lifespan, lowering their mortality. So this is a simple model that we're starting to pull together. And basically, as I say here in the box, there are two ways to bloom. You can grow fast or you can live a long time. And the growth rate is clearly regulated by phosphorus and also light and mixing dynamics of those things. And that's all important. But we think that the mortality term there is a function, I say zooplankton here, biomass, but also benthic mussels are undoubtedly important as a mortality term. And the biomass of those filter feeders is important, but so is the toxin concentration in the microcystis. And there's a fair amount that the actual relationship between grazing and microcystis is not particularly well known, microcystin, but we do know that with increasing inorganic nitrogen supply, the organisms produce more of the toxin. So there's a reason to be looking at nitrogen and seeing how that might be changing over time. The Finger Lakes are all pretty naturally nitrogen rich. Nitrogen's probably increased over time, but the native bedrock is nitrogen rich. Nonetheless, nitrogen levels have gone up, and we are speculating that the direct input of ammonia might play a role as well. So we've been looking particularly at the input of ammonia to Skaneateles, directly to the lake and to its watershed, since about 2021. And we've been looking at the Connecticut Hill monitoring station, NADP monitoring station for ammonia since 2008. And for those of you who don't follow atmospheric deposition much, that station is one of the oldest continuous NADP monitoring stations in the country. It was set up originally by Gene Likens when he was at Cornell and has been run by Tom Butler since 1976. So long historical data set there, but ammonia wasn't measured until 2008, and ammonia is still undermeasured, understudied across the country. So we use passive samplers to measure ammonia, and this shows a little upside down cup there. It's just a a filter inside there that absorbs ammonia gas onto it from the atmosphere. We put them out for 2 weeks at a time, we being Tom. And then the analysis is done by the NADP lab in Wisconsin. And what else do I need to say about nothing, probably? We've been measuring, again, at multiple stations across the Skaneateles watershed, but also at this long-term monitoring station. And here, if we're looking at the ammonia concentration over time from 2008 to 2024, and you can see that it's going up. This is a regional signal. We don't entirely understand why the ammonia is going up. I can try to address that a little bit if people have questions either after the talk or over lunch. I think it's a very interesting thing. Our stations in the watershed for Skaneateles are shown here, and we have several in the southern part of the lake, the less developed part of the lake, and several in the northern part, just more developed and also closer to some of the upstream, upwind agricultural sources. We also have some data from sites in Owasco, but I won't go into any detail on that today. So this is our first year's worth of deployment. We started in May of 2021 and went for basically a year, so you can see a strong seasonal pattern. We're showing each of the sites here. They all sort of track one another, but the concentrations are significantly higher at some of the sites than at others. There's a lot of interesting data in this temporal trend, and again, I can go into that in questions if you'd like. Based on these initial results, we're able to get some renewal funding for a more extended campaign, and this shows all of the data. So starting back there in May of 2021, and we finished sampling this past May. The blue line there at the bottom is the regional signal from Connecticut Hill, the NADP monitoring site. All of the sites in Skaneateles are higher than that, some of them a great deal higher. They all show the same sort of seasonality. Now these are concentration data. What we want to know is the input to the watershed and directly to the lake surface. And to get that, you take the concentration and you multiply it what's called a depositional velocity, and you have a flux rate. And for depositional velocity, this is where our colleagues from the EPA have played a role. We're showing here by week number, so starting in January, over a year. Most of that top curve there is our estimate for the depositional velocity for the lake surface, and there's some seasonality there that's driven by wind. The depositional velocity is higher when it's windier. The other curves are pulled out of the EPA CMAQ model for what the depositional velocity would be in this area at any particular time. Strong seasonality in that as well. A lot of that is driven by humidity and also by canopy cover of trees, which will increase absorption. So we use these estimates times our concentration data to come up with estimates of flux. And here are our estimates. We're looking here averaged over time for an annual average deposition rate for each of the sites in the Skaneateles watershed. The red are our estimates based on our measurements. The blue bars are what the EPA would estimate the input is based on their national CMAQ model. And on the far right is our estimate for the direct deposition to the lake surface itself, which is higher than anywhere in the watershed. So a take-home point here is that there's a lot of spatial variation across the watershed, and our estimates are all, almost all, higher than what the EPA classically would think. So it's a pretty high input. Another way to look at that is we're looking here at the direct inputs of nitrogen from the atmosphere to the lake in 2023 on an annual basis. And both of these bars are based largely on the EPA, CMAQ, and TDEP models. But the difference between the left bar and the right is that on the darker bar here on your left shows what the EPA, dark blue there, would think for the direct gaseous ammonia input to the lake. And the stippled bar on the right is based on our estimates with real data for ammonia concentration. So again, EPA has historically been underestimating the ammonia input. It's quite substantial to the lake. The other major bars there, the biggest points are ammonium, the ionic form in wet deposition, and nitrate in wet deposition. So from that, we can put together a nitrogen budget for the lake inputs. And the direct deposition to the lake from ammonia is 18.3 metric tons of nitrogen per year. Other reduced species, ammonium ion, are lower at 12, and the oxidized inputs are 11. So the major input directly to the lake is in fact ammonia gas. We also have substantial nitrogen deposition to the watershed. The ammonium there is 67.4 metric tons. Other inputs are lower. And we have an estimate of what NANI, that's nitrogen use for human activity in the watershed would be. So agriculture as well as oxidized nitrogen inputs and use in human food, sewage inputs, things of that sort. And from that, we can estimate what the watershed load is. So overall, the watershed load is greater than the direct deposition, but the direct deposition to the lake surface is high. And again, a lot of that is as ammonia, which is extremely biologically available. So indeed, if the cyanobacteria are using that to increase their toxin load, that number is important. Now we took one more step and tried to look at where the ammonia is coming from. And for that, we used the NOAA high split model. So on the left here, you're looking at the lake, and the red dots are CAFOs, confined animal feedlot operations, large ones, and these are all large dairy farms basically. And also shown are our sampling sites. So we're using a high split model to look on a real-time basis for the time that our samplers are out there over 2 weeks. We look at the wind on a real-time basis, look at where the wind has been coming from 1 hour before it hits our actual samplers. And if it's coming across one of those CAFOs at that time frame, we call that a hit. And we can then plot the hits as a function of the concentration that we're seeing for each of those times. And the most convincing part of this plot is on the far right over there, which shows our data for the summer. The ammonia concentrations are higher in our samplers when the wind has been coming more over CAFOs. So it's an agricultural source. In the fall and winter, it's less convincing, same trend, but of course the deposition is lower. And then we have that little messy plot up there in the spring, but it turns out that the late spring numbers look just like summer and the early spring numbers look just like winter. So the bottom line is when the wind's coming over CAFOs, there's more ammonia going into the lake and into its watershed. And that has been going up over time. So that's my ammonia talk. I just want to end with some information, not going to show any data on this, but we've been working with a series of colleagues, mostly from Canada. Irina Creed from the University of Toronto is the lead on this, working with Josh Teenpoint from York and John Small from Queens. Several of us from Cornell got them interested and engaged in it. And we're also working with Anita Dedick from Mostar University in Herzegovina, and with Doug Young, who's the owner of Spruce Haven Farm. And we cored 6 of the biggest Finger Lakes back in June at fairly great depths. You can see the cores there. This is mostly Joshua Teenpoint's ability. We've taken those and sectioned them in the field at half-centimeter levels, and we have already dated them. We can share those data soon. We have data on chlorophyll from all of the lakes. We have data also so far on one of the genes that's a major precursor to producing microcystin over time, and we'll be sharing those data as they come along. We also intend to measure the microcystin toxin itself. Phosphorus, we'll be looking microscopically at when microcystis came in. We'll be looking genetically at when microcystis came in. These lakes are all historically under-monitored, but we're hoping this will provide a background record across the Finger Lakes on that. And we'll be very happy to share any of those data as they come along. I want to give a special shout out here to Doug Young, because he owns one of the CAFOs that we think is responsible for this ammonia and maybe aggravating the blooms. He really wants to know if that's true or not. And when he found out that we wanted to sample these lakes back in June and that we needed a boat, he volunteered his boat, which is the one there, and he towed it from lake to lake for us and piloted us with great skill, allowing us to take these cores by hand at water depths of well over 100 meters in some cases. So anyway, very proud of that. So that's my talk. We're funded by the USDA Hatch formula funds to Cornell, and also by the gift from Mr. Atkinson that supports my salary and other activities in our lab. And we have to thank a lot of people for giving us access to their land, for putting on ammonia samples, including Charlie Driscoll. So thank you, Charlie. Time for questions? I'm told there's time. No questions? Yeah, in the back there.
What do you think the residence time of ammonia is in the lake once it's deposited? How quickly does it get oxidized to?
Well, it's probably has a very short residence time, and I won't say exactly how long, but I think minutes to hours, not days to weeks. And it's the more like I think it's more likely to be taken up biologically by the phytoplankton as opposed to oxidized. I mean, there are organisms that'll oxidize it to nitrate if nothing takes it up faster, but they tend to be pretty slow at that in a system like this, particularly in an oligotrophic setting. So very short. It's highly labile. And of course, one of our thoughts is that it might make it easier for the microcystis to produce the microcystin. I have to say that there's not a lot of strong lab data on that. The few studies where people have looked at nitrate versus ammonia, it doesn't really seem to make that much difference, and yet it seems like it should theoretically. So I'm hoping more people will get interested in doing it, but it's a significant input. Good question.
Hi, it's Lewis McCaffrey from New York State Department of Environmental Conservation. Thank you. That was a fantastic presentation, Dr. Howarth.
Thank you.
I wondered where you got the information about all Finger Lakes are nitrogen rich. We don't see that constant across the lakes. That was one question.
Okay.
The other was, have you tried looking at nitrogen isotopes for source identification?
Yeah, no, both good questions. On the isotopes, no. We have not done that here. My lab has historically done it in coastal systems and elsewhere, but not in the Finger Lakes. And I'm not aware of anyone who's done that yet in the Finger Lakes, but that would be a very important thing to do. As to
Great idea.
The data on the nitrogen-rich lakes, it's coming in part from your CSLAP monitoring and others. But the nitrate, if you look at particularly the inorganic nitrate to SRP ratios, it's on mean values across the lakes always more than 1,000 to 1. TN to TP is lower, it ranges from like 120 up to 300 to 1 or so, but I think it's the inorganic ratio that's more informative there.
Thank you.
Bob, great talk. Thank you very much. If you will, and if I've got time, maybe two quick questions. One is, and this is just sort of speculation, but at our site, we measured deposition, wet and bulk deposition, and I find actually surprisingly high concentrations of phosphorus in that. And I wonder if you had any thoughts on phosphorus sources. It would be largely in a particulate form, but from CAFOs, and do we know much about that? And then the other question is, I mean, the atmospheric chemistry has changed a lot over the last couple decades with declines in sulfate and nitrate, and that's going to influence the processing of ammonia in the atmosphere. Right. So could you speculate on how those changes have altered the transport and availability?
Those are both great questions. I don't think there's much data to suggest that the ammonia input to the atmosphere has increased all that substantially in our area over, say, the last decade or so. So ammonia concentration's going up, but not necessarily the inputs. Could be due to changes in farming practices, but I think a lot of it could be, as you say, because the atmospheric sink has gone down as sulfur's gone down. The residence time of ammonia in the atmosphere might be longer. It's also related to the weather. Every time it rains, it's going to strip all the ammonia out. It's related to the humidity, and those things are changing. So I think there's some great research that could be done on that. I don't have the final answer, but I alluded to the fact that we don't really understand why that's going up. I don't think it's a simple source attribution. On the phosphorus, we didn't measure it. I think it could be very important. It could be, it's going to be particulate, as you say, and one culprit could be dust from plowing and all. But I think there's some evidence too that pollen can be a big source of particulate phosphorus as well as nitrogen. And, we'd have to look microscopically to get at that probably.
Yeah, very few measurements of atmospheric deposition of phosphorus.
Very, very little. I think it's an important point. And probably pretty labile too, although it depends on what if it's pollen, it'd be less so than if it's agricultural soil ending up in the lake that way. Great, thank you.
Okay, next up we have Dr. Greg Boyer from SUNY ESF. Hi, Greg.
It's kind of nice going later in the talk because I can rewrite everything after I hear what other people say. I want to introduce the research team here. This is a project we just started last year in 2025 with funding from the NAPI Foundation, and we appreciate that. Dominique and Emily are both here in the audience, so feel free to ask them any questions. Zach's running all our cyanobacteria toxin analysis, and Anne's been helping us out in the lab. Just a quick bit of review. Our real question is, why are we getting blooms? And I think that's everybody's questions. And the thing you need to remember about a cyanobacteria bloom is there are 5 or 6 things that are important for the bloom to happen. You have to have enough light. You have to have a warm enough temperature, someplace above 12 to 15 degrees, and you have to have calm winds so that they can control both float to the surface where you can see them, but it's also very important that Microcystis is actually a low light adapted species. So if it floats to the surface, it gets sunburnt. And so it actually needs calm enough winds that it can control itself in the water column in order to not get too much light. Mike talked a little bit about these physical parameters. I'm not going to talk a lot about them. You obviously need a source of food, nitrogen and phosphorus. And then you need seed population, and there's this whole question about zebra mussel grazing. Dominique mentioned a little bit about the zebra mussel grazing. The seed population since 2017 is a non-issue because we've had a massive bloom, so there are seeds in that lake for any bloom that we ever want to have. So I'm going to focus on nutrients. And we really had 2 questions. The first question was, what's happening in the lake, in the algal population before the bloom? I sort of like to use the analogy of a car wreck. If you see a car wreck, the bloom, you're not going to know what led to the wreck, right? You got to look at what happened before the bloom to understand why the bloom occurred. And so we approached this by doing weekly sampling at 3 sites, and I'll talk to this. And then the second question was really more, we assume these blooms are regulated by nutrients and physical conditions. And so if nutrients are important, what nutrient is actually driving this? And I'll talk a little bit about nutrient levels and what nutrients drive the bloom. So let's go to question 1. This is the weekly sampling looking at populations in the lake. And we picked 3 locations. We had the Sailing Club down on the eastern side. We had the Country Club Pier up here, and then what we call the North Shore site, which is basically right outside the Skaneateles Lake office off their breakwall. These were chosen, not necessarily the best sites in the world, but they were chosen because they have a historical report of harmful algal blooms, so we thought we might get a bloom at that. More importantly, we could get to them easily because we had to be able to sample all 3 sites at basically within 30 minutes of each other. So we had to be able to get around to the lake to get a quick snapshot. And we had to get them back to the lab within an hour or an hour and a half for processing because we knew there was a holding time on some of the measurements that we were looking at, right? So we collected weekly samples from June through October through these 3 sites. And this is some of the data. Once we took these weekly samples, we brought them back in the lab and we ran them through an instrument that's called the fluoroprobe. And the fluoroprobe, what it'll do is it'll give you the total chlorophyll in the algae, and then it'll break that chlorophyll down into how much chlorophyll is associated with green algae, how much chlorophyll is associated with diatoms and dinoflagellates, and how much chlorophyll is associated with cyanobacteria. It gives you a few other things too, but that's really what we were interested in. And I'm going to show you a bunch of graphs. They're all set up the same way. On the left side is the average of the 3 sites. And so if you see really huge error bars, what that tells you is the 3 sites were not necessarily all doing the same thing. And then on the far side, you'll see the 3 sites shown individually, right? And so you can see here, starting in June, running through October, the chlorophyll in the water column is pretty low, and Bram talked about this too. Satellite imagery also shows this. The chlorophyll in the water column was pretty low, but it gradually is increasing over the course of the season. If you look at the individual sites, you can see there's more dynamics there. And I want to call your attention to 2 sites on the North Shore that I've got marked with August 5th and August 12th. And you can look at this site and you can say August 12th is higher than August 5th. So this bloom is going up. But you get a very different interpretation if you start to break it apart. And so this is actually looking at just the cyanobacteria channel in there. And you can see cyanobacteria start showing up around August 5th. They gradually increase up through September. But if we go back on that North Shore site and we focus in on August 5th, you can see on August 5th, we have a huge peak in cyanobacteria. Well, it's not huge, it's 1.5 micrograms per liter, which is pretty darn low. But anyway, we have a peak in cyanobacteria, but by August 12th, even though the total chlorophyll is much higher, cyanobacteria have dropped out of that sample. And that chlorophyll that we're seeing on the 12th is totally due to green algae. There's very little contribution from the cyanobacteria. And it points out some of the difficulties you run into when you use an integrative measure like total chlorophyll to try to understand population dynamics amongst different species, because they actually behave quite differently. You also see we got a very nice bloom at the North Shore on late in September, and I'll talk a little bit about that. Okay. What happens with cyanobacteria toxins? Of course, I'm a toxin lab, so we have to run our cyanobacteria toxins over this. And you can see cyanobacteria toxins. And by cyanobacteria toxins here, I'm talking about microcystins, the liver toxin. We measure the neurotoxins and all sorts of other things. They are all absent. Fortunately for Skaneateles Lake, it's purely dominated by microcystis, which produces a single type of toxin, a single class of toxin. But you can see there are peaks and valleys in the toxin production. And you can see that on the left side, you can see the 2 peaks have huge error bars, and that's purely because the North Shore had a very toxic bloom versus no toxins found off of the Sailing Club or the Country Club. And it again points out some of the problems that you have when looking at different sites. These blooms can be very localized on where they're happening. Just for kicks, we took the cyanobacteria chlorophyll and we took the toxin concentrations, and you can calculate what's called a cellular quota. Normally you would do that on toxin per cell, but you can also do a chlorophyll-based cellular quota, so you get amount of toxin per cyanobacteria chlorophyll. The cellular quota for toxin per cyanobacteria chlorophyll was about 0.12. And very interestingly, throughout the whole mid part of the bloom, it was pretty constant. And so there was very little variation in the toxin per cyanobacteria chlorophyll. We know these blooms are dominated by microcystis, right? We know that in culture, microcystis has a toxin per chlorophyll ratio of about 0.1 to 0.15. And so what this tells us is that the changes in toxicity that we're seeing here are much more a reflection of the changes of biomass in the column. We're seeing more toxin because we have more cyanobacterial biomass, and not more toxin because we're shifting from a less toxic to a more toxic species. All right, so here are my take-home messages. Chlorophyll levels in Skaneateles Lake showed a general increase from June through late October. I didn't actually point out, we also have temperature sensors in the water here that are measuring at 15-minute intervals. So during the early part of the season, the average lake temperature increased from 13 degrees, that's really below that 15-degree threshold, up to about 26 degrees in July, and then it sort of stabilized for a while. It sat around about 26. All that earlier chlorophyll growth is dominated by green algae and diatoms. You get around August 5th, the cyanobacteria bloom starts, and it runs up through about October 8th. Very interesting and not what I expected. The temperature in the lake is actually decreasing at that point in time. So it's going from 26 back down to 19. So it's not that we're getting more cyanobacteria because the lake is warmer. It's that we're getting more cyanobacteria because we're above that 12 to 15 degree threshold for a longer period of time. Right? Dominique talked a little bit about this when she talked about that 15-degree threshold. This is a really important concept now when we start talking about bloom dynamics. The blooms are dominated by microcystis. I'm not going to say much about that. Toxin concentrations were variable and low. And we talked a little bit about the toxin quota. Frank very nicely gave us 3 very high toxicity blooms that occurred in Skaneateles Lake. We looked at those also. The toxin quota and those blooms, very similar to what we saw. They're all around the 0.13 to maybe as high as 0.5. So we're not seeing a more toxic species, we're just seeing more cyanobacteria in the water column. All right, let's move on to the fun stuff, the nutrient stuff. So we really wanted to know what nutrients are driving the bloom. And so the way we did this is that we would go out in the bloom and we would take 50 some odd bottles and we would fill them with lake water, and we would spike 12 of those bottles with 5 times the ambient concentration of nitrogen. We would spike 12 of those bottles with 5 times the ambient concentration of phosphorus, 12 of them with both nitrogen and phosphorus, and then 12 were left by themselves. And we would put half those bottles out in a cage and we would float it out in the lake, and we would come back after 3 and 7 days and collect half of them. And we'd take half those bottles and we put them in an incubator in the lab under optimal conditions of light, temperature, and no wind, right? And then we'd analyze them again by the Flora probe for toxins, and for the phytoplam, which was looking at photosynthetic efficiency. I'm not going to talk about the phytoplam at all, just for time reasons. Okay, so here's a picture of what it actually looks like. This is Dominique sitting out on the dock. You can see the 50 bottles spread out there, which she is diligently adding water to, and then going through and spiking. They're all color-coded with little zip ties around them so we know who is what. They get flipped upside down in this cage. The cage gets sealed with a whole bunch of zip ties. We went through, I think, 300 zip ties over the course of the summer because you have to cut them off and throw them away. They go on the little buoy that's off the top. This is on the Ben Wiles Pier, and they get pulled out, and then they sit there, and we come back. All right. This is the North Shore sampling. Total chlorophyll in blue, cyanobacteria chlorophyll in green. This is the same data that you saw before. The only thing is the red dots I have put on where we did the nutrient experiments. Now, recognize we did the nutrient experiments off the Ben Wiles Pier. This was sampled along the North Shore. They're not exactly the same site, but you can see in most cases they agree pretty well. And the position of the orange dot is actually the total chlorophyll in the control sample when we started the experiment, right? So I'm only going to show you results from 3, a pre-bloom experiment, an early bloom experiment, and a late bloom experiment. So here we are in the pre-bloom experiment. And again, everything's set up the same way. At the top, you'll see the control, the plus nitrogen, plus phosphorus, plus nitrogen and phosphorus using the total chlorophyll. This is all in the lake. The next one over is going to be the green algae. The next one down here is going to be diatoms, and the next one over there is going to be cyanobacteria, and we'll go backwards here. We're in June. There's no cyanobacteria in the water column, so we're not seeing cyanobacteria using the fluoroprobe. That's not saying it's not in the water column. You actually can see it in net tows. It's there, but it's below what we could measure using the fluoroprobe. If you look at the diatoms, you see the diatoms are stimulated by phosphorus, and the addition of nitrogen really doesn't make that much difference. Same thing is true for the green algae. They're stimulated by phosphorus. Nitrogen really doesn't make that much difference. And so we have a classic phosphorus limited situation at this point in time. If you move into the pre-bloom or the early bloom, well, now it gets a little bit more complex. Right? If you look at the chlorophyll, you see a certain amount of stimulation from phosphorus, but you see even more stimulation if you add phosphorus and nitrogen. Nitrogen by itself doesn't have effect. So what we have now is we have shifted into a co-limited lake where we are being stimulated both by nitrogen and phosphorus. Right? Green algae, very classically co-limited. Diatoms, interestingly enough, still don't really care about nitrogen. They're still phosphorus limited. But if you shift over into the cyanobacteria, you see the cyanobacteria are strongly co-limited, and they grow much better with nitrogen and phosphorus than just with nitrogen or phosphorus by themselves. If we move later into the lake, it becomes interesting again. Green algae are still co-limited. Diatoms have started to move into a co-limited situation. And the cyanobacteria at this point in time, they don't care about nutrient addition anymore, right? So whatever nutrients they need, adding more nutrients doesn't really change their growth pattern. And my original thought was, well, we're missing a nutrient. We have copper or iron or something like that. But in the little tiny corner down there, I showed you the results of the lab experiments where we've growing them in the lab under optimal conditions, right? They grew great in the lab under optimal conditions with nitrogen and phosphorus. So this tells me that we're starting to move into the situation where physical conditions are starting to become more important about what's controlling this bloom, right? We were very interested in the impact. There's some studies that we've done, some molecular data that we have that suggests that cyanobacteria actually have some unusual nitrogen nitrogen utilization pathways. And this whole question about you get more nitrogen, give you more toxin, et cetera. And so we decided we would try to sneak an experiment in between these two data points where we looked at the type of nitrogen that we added. If you look at the green algae, you can see green algae, they grow fine with nitrate, they grow fine with ammonia, and they grow fine with urea. So they can easily use all 3 forms of nitrate or nitrogen. Diatoms, interesting, didn't like ammonia. So for some reason, they definitely did not grow well in our ammonia addition. And the cyanobacteria, they're equal opportunity consumers, right? They can use just about any nitrogen form that got stuck in there. So if we gave them arginine, we gave them nitrate, we gave them ammonia, or gave them urea, all of those were fine for causing increased growth. All right, so here's our take-home messages from that second part. Diatoms and green algae, early in the season, were limited by phosphorus. Nitrogen addition, with and without phosphorus, had little effect. Cyanobacteria just aren't there, so we don't have to worry about them. As we start to move into August, Skaneateles Lake shifts from a phosphorus-limited lake to a co-limited lake. This is very pronounced for the cyanobacteria. Cyanobacteria were strongly co-limited by nitrogen and phosphorus. Much less so for the green algae, and there are reasons, we can talk about that, and not at all for the diatoms. Diatoms remained phosphorus limited at that point in time. By September, we're still into a co-limited state, but now the cyanobacteria, they aren't responding to added nutrients in September at all, right? So we're not seeing any increase in growth, right? By October, I didn't show you that data, but we've moved back to basically to June, where cyanobacteria are gone at that point in time. Diatoms are phosphorus limited, and the green algae source still remain co-limited, right? I didn't show you the data on toxic quotas, but we did these nutrient spike experiments. The toxin quota throughout these different nitrogen forms ranged from 0.1 to 0.15, which is basically the same toxin quota that we saw throughout the whole thing. So the different forms of nitrogen did not increase more toxicity per cell, and the amount of toxin you got was purely amount due to the biomass that was there in the thing. The one caveat I put down here is we just started this project. We've got a grand total of 1 year of data, and phytoplankton populations are hugely dynamic, so it's really difficult to make definitive conditions on 1 year, especially when you're trying to compare nutrients and physical parameters. So we definitely are going to need to repeat this, and we're going to make some modifications, but we're also open to suggestions. But I do want to point out that one of the key take-homes here is when you start talking about these algal responses, total chlorophyll is sometimes a very imperfect measure because the different classes of algae have very different biochemistries, and they respond very differently to different inputs and parameters. And so I'll stop there. I didn't put a summary slide. I didn't put a thank you slide in, but anyway, I'll stop. Sure.
I was very happy with this presentation, Greg, because I tried to connect the dots that I achieved through the remote sensing analysis, and that's nicely overlapped with what we have achieved, but I didn't know the reason. For example, you mentioned that decreasing the temperature, the total algae is increasing increasing. So there is really no relationship between that. But you explained it nicely that it is because already has above the 15 degree or 12 degree, whatever it is. And then we saw the satellite data shows that the increase of total algae from early in August all the way to early October, then it's dropped. I know that you didn't collect data after October, but starting from mid-October to end of November, satellite shows decreases. So I mentioned that because I think remote sensing can somehow address the caveat you mentioned. The model now have been developed, we can backcast it to all satellite data since 2014, since Sentinel-2 is available, and then generate the map and total chlorophyll for that, and then bring it to you for interpretation and see how this trend works. Sure. So that's good. Thanks.
Okay, last but not least, Dr. Christine Georgakougas from SUNY ESF.
Thanks for hanging on, everybody. I know we've been sitting down for a little while and are trying to go to lunch, so thanks for continuing to engage with us. First, I want to say this is a big project. Bahram and Greg and everyone are all involved, so hopefully we can eventually tie all the data that we'll get into those ones. The folks that are most acutely involved in this one are Rakesh, Dominique, and Steve, so if you're having lunch with any of them and have questions, feel free to ask them as well. I think everybody is equally informed about what I'm going to talk about. So when we think about Skaneateles, I think we think a lot about our recreation users. We think a lot about inputs in terms of surface water. We've heard a lot about atmospheric deposition today. But I want to thank the person who asked the question about what are those other inputs? What are the septic users doing here? And that's sort of what we're trying to get at with this one. They're sort of an interesting anomaly. They are, you could consider them a point source. You could consider them a non-point source. A lot of these systems have been there for a long time. Some of them are newer. There's a lot of diversity in how they were installed and where they are in the landscape. And so our question here is really, what are those have really high septic density? Are they sort of homogeneous around the lake? Is it controlled by other landscape scale factors, that kind of thing? And I will go ahead and say that I'm not going to share any data today. We're still in the process of analyzing and collecting this stuff. So again, during lunch, if you have ideas for us, happy to engage in those types of things as well. I want to thank Dr. Lewis McCaffrey, who created this map a little while ago. Thanks for sharing it online so we can use it here. This is a summary of where we are in the watershed. So the colors represent Skaneateles watershed. The reds are those areas of higher septic density. The greens would be those areas of lower septic density. You'll notice that things are not necessarily homogeneous. So if we sort of draw a line in the middle of the lake, we have those more areas of higher septic density on the northern end of the lake, with some areas, this is the town of Scott down here in the bottom, those like more rural spaces that don't have that consolidated wastewater treatment, but do have a lot of residences. You'll see high septic density there as well. But I also want to draw your attention to the diversity as you move in towards the lake and away from the lake. We have really high septic density right on the lake shore, and that density decreases the farther away we go. That also is controlled a little bit by the geology of the system. Down on the southern end of the lake, we have really steep walls of our lake, so you can have like one house wide away from the lake, whereas on the northern shore, you can have sort of more homes closer together, closer to the lake, and so that's part of why you see this really high septic density up in the northern end, and that lower density, though you'll still see some of those sort of a solid black line all the way around the lake, right? We enjoy that lake shore living, and so that's where this stuff is coming from. I'll also note that these dots are at the center of the tax parcel. So this is a publicly available data set. So anybody who noted that they have on-site wastewater treatment is noted here at the center of the tax parcel. These dots do not represent exactly where those septics are located. Those are a little more nuanced. I'll talk a little bit about that in a second. So if we take a step back to just sort of understand what is happening in on-site wastewater treatment, whether your home is located right on the lake shore like this one or farther away, most of those are pumping their wastewater to a septic tank that is a little bit farther away from the lake, allowing any of the contaminants that are in that wastewater to be microbial degraded within the tank, within the leach field, in the soils around the leach field before it hits any sort of surface water. So in an ideal functionality, you have very limited nutrient or contaminant transport because the soil is acting as your filter. Similar in reverse order as you would think of it as a groundwater well. The soil is filtering out any contaminants that we might not want to go anywhere. If you think a little bit about different types of contaminants, that soil is going to act as a more effective filter for different types of contaminants. So sort of like Ryan was mentioning earlier, phosphorus tends to bind with sediment particles. So hopefully those soils are acting to filter out a lot of the phosphorus before it reaches our lake from these septic systems. Whereas if you're thinking a little bit more about contaminants like nitrates, nitrates tend to be more dissolved in solution. Those ones, the soils are going to less effectively filter them out, but could be microbial degraded instead. So depending on the contaminant that you're thinking about, it really matters. Is the soil going to effectively filter those things out of the system? Phosphorus and nitrogen are one that we talk a lot about with algal blooms, with Skaneateles Lake, but I'm going to go ahead and say that there's a lot of other contaminants going in here. Frank mentioned this at the beginning. My group thinks a lot about pharmaceuticals and personal care products and other cleaning detergents and things like that. And each of those also functions in different ways. So some of those act more like phosphorus, and they're going to absorb really strongly to your soil particles. Some of those act more like nitrogen, and so they're going to be passed a little bit more easily through these systems. Our goal here is to try to understand, are these septics, are our nearshore inputs higher in these areas that have a lot of septics, or do we see sort of similar patterns around the lake? So to try to answer this question, we've input a couple of different monitoring stations. One is a shallow surface water well right at the edge of the lake. So before any water that's coming off of your landscape in the subsurface hits the lake, we'll take a sample and see what's in that sample. We're going to look for a whole bunch of different things. I'll show you what those things are in a little bit. And then we'll also take a near shore lake sample. So if we see really elevated stuff in the groundwater samples, do we also see that right near the lake shore? Or is it diluted enough so that we don't sort of see those in the detection methods that we're using? The other question, though, is about the filtration of the soil, the filtration capacity of the soil in these systems. So what we really need to know is how effective are they, how many of these contaminants are being held in those soils right before it hits the lake as well. So we also have, sorry, I'm holding too many things. We also have two other sampling sites here. One is a subsurface sample where the groundwater table will be, and the other is a surface soil sample. And we'll extract a bunch of different contaminants from each of those things as well, try to see if we see at the groundwater table, do we see really elevated levels of phosphorus? Do we see that you can absorb more phosphorus onto those soil particles? And then same thing for some of those other pharmaceuticals and personal care products. Do we see that those soils are already sort of saturated? Are they at their extent of absorption potential, or can they continue to take on these things? For those of you who engage with septic tanks around Skaneateles Lake, a lot of these septics are very old, right? They've been in place for a long time. They've been fixed and added and adjusted to suit the needs of our current homes. But the systems and the places where they are the same. And so the question sort of becomes, have we saturated those soils? And is that level of saturation enough before it hits the lake? Or do we still have that sort of buffer zone or far enough away before any of these things get down there? So we're trying to take this sort of dual approach, water samples, soil samples, to try to address this question. What does it look like? What if you were to input one of these wells, and thanks to those of you who are online or in person that have one of these wells in your residences, we dig a nearshore well down until we hit the groundwater table. So the idea is that we want to make sure that that well is wet when we want to go sample. In general, that's something like 2 to 4 feet if it's right near the lake shore. I will say that the Skaneateles Lake water level is a little bit complicating of our analysis here. Sometimes we dug a well and then the lake level drops and our well no longer has any water in it. So we're adjusting some of those techniques to try to make sure that we can get samples all year round. We drop a PVC perforated pipe down in there with a water level sensor so we can figure out what is the depth of the water table throughout the year. It'll be continuously monitored. And then we install this protective casing around it so that, number one, our well doesn't move around too much, and then also so that people don't step in it and hurt themselves as they're engaging with the lake in the ways that they're recreationally or otherwise. I will put a plug that we're looking for other folks to install some of these things. So if you're jazzed by this and want to engage, please chat with any of us at the beginning who are involved in this project. And I will say that we're looking at a whole slew of different contaminants here. So those primary ones, nitrogen and phosphorus, are the ones that we usually think about with algal blooms and stuff like that. But I will say that these pharmaceuticals and other products they have many functions. So antibiotics, though they are intended to interact primarily with bacteria, they also have interesting effects on other organisms like aquatic macroinvertebrates. They increase stresses on larger fauna such as fish and things like that as well. So those untargeted byproducts are interesting in terms of what's happening to the ecosystems of the lakes that we're in. But then also other things like artificial sweeteners are also antibiotics. And so we use these things for one purpose, and then they enter our ecosystems and do something else and do those changes and engage with our algal communities, like you've heard everybody sort of talking about today. Are those some of the triggers that turn on or turn off which populations are more able to adjust and modify their life stages based on the stressors that they're experiencing? Paired with this also, we'll do some fecal indicator bacteria analysis and some antibiotic resistance gene stuff. So trying to pull in some of those more biotic factors as well as the abiotic stuff. And then we have a whole slew of water quality metadata that we're taking alongside. So with that, I'm happy to take, hopefully this was pretty short. People can ask as many questions as you want. Again, if you know folks who are excited to have a small well installed on their residence or a place close to, and it can be have a septic, it can be on a sewer shed, it can be any of those diversity of wastewater treatment that we have. And then lastly, I'll just give a shout out to all the undergrads, both at ESF and at SU, who've been helping collect all this stuff in addition to the folks on that front page. Yeah, so hopefully I have time for some questions.
Thank you for your presentation, Christine. I'm curious, are you considering looking at any dependencies between your observations and the condition of the upstream septic system, maybe the age of the septic system or the style of septic system?
Yeah, absolutely. Great question. Yes, we're trying to get all of that data. So if I will say that the diversity of that data that the residences have is not consistent. So any of that stuff that is available, we are open to. So we're trying to get a whole range of septic systems across ages. So think about a very new septic system probably works very differently than a septic system that's been in place for 50 to 100 years. We have 7 sites so far that span anywhere from, I think 10 years is our youngest, to over 50 years. So anywhere in there is what we're looking for. We also have a pretty diverse range of the types of systems. So a bunch of these are pretty old systems that are designed to be leaky. So they're not necessarily sealed tanks, but they're supposed to sort of like emit into the landscape a little bit. Whereas some of the other ones are more like PVC piped style perforated pipes that go into a built up leach field that are then going to engage in the soil microbiology in a pretty different way. We're looking for all of those things. So trying to get sort of the whole spectrum of different types of wastewater treatment that happens on site. I will say that Skaneateles Lake has a pretty diverse range there. There's a lot of folks that do more cesspools, so collect wastewater but do not treat on site. It's pumped out and treated elsewhere. There's also things like composting toilets and stuff like that, as well as these a couple of homes contributing to a single septic tank and then distributing to in a larger system like that, depending on what's available in terms of landscape. So yeah, there's a huge diversity of wastewater treatment stuff that happens, and I'll say that we're excited about all of them, so don't hold back if you know folks that are willing to engage. Yeah, Liam.
Hi, Christine. I was wondering if you have done any sort of kind of back of the paper napkin math on if it is reasonable to assume that the soils are fully saturated with phosphorus. I'm kind of imagining the soils as sort of like a sponge, and you're having your leachate field slowly saturate that sponge. Given, we're looking at probably 100 years or so of length for some of these sites, is it reasonable to even assume over a certain volume of soil that they are fully saturated or not?
Great question. I don't know the answer to that. What I would propose is that I think we should do like a phosphorus addition experiment to see how much more can the soils hold. I will say that a lot of our lakeshore sediments are very gravelly. So think about like large particle style soils that are often washed down off the landscape. Those types of soils don't have very many adsorption sites. So something like smaller sediment particles should have more adsorption sites. So it's going to be really soil specific. And we definitely need to do that calculation in the form of a lab experiment to figure out what's going on. Unless somebody else here has done that and would like to share. Cool, thanks.
Just a few announcements for our folks online. That does conclude our online session for the morning. We will be moving into lunch and then breakout sessions with folks here at the conference. But wanted to thank Christopher Bakura and Molly Schultz, which have been part of the technical team, making sure that the online experience has been as great as it is. So thanks a lot to ESF and all of that, and Steve again, and Charlie. I did put into the chat a few upcoming events. We're loving this science. It's been jam-packed today. There are some events coming up that I will make sure that there'll be follow-up on this conference, this summit, with info about the recordings. We'll be connecting with the presenters on what they'd like to share with their slide decks, but get more information out to all the registrants that have been part of this. Wanted to say thank you to all of our presenters and everybody that's participated with the wonderful questions today too. But the events coming up, the first one is the Bob Brower Symposium that the Owasco Watershed Lake Association hosts. It's Saturday, March 14th from 9 to noon. Great event, highly recommend that. And then there is the New York State Federation of Lake Associations annual conference that is on May 8th and 9th up in Lake George. Actually the first one coming up, I'll back that up, January 29th at the Finger Lakes Institute at Hobart Williams Smith is the Finger Lakes Research Conference that's coming up very soon. Early bird deadline's January 15th. And then the other one that Steve's been a great part of is the fourth annual meeting for the Healthy Waters Solutions. And that will be May 19th through the 21st. Registration's not open for that, but if there are folks that are interested in presenting, the deadline is tomorrow for proposals. So that's all I have for those announcements. Thanks again. Enjoy lunch. Looking forward to more discussions. And thanks for everyone who participated online.
Yeah, thanks again to everyone presenting. Thanks for the participation. We'll meet back here at, we'll say 1:05, 40 minutes, to do breakout sessions this afternoon.
Just a note on all of the eating ware that you're using. Everything should be compostable if you got it here, except for the plastic cups, which are recyclable. If you got your stuff somewhere else, then look close and see if it's compostable or not.